+2 for questions. The timer is for the total 10 minutes. So once you get down to the 2-minute mark, you should wrap it up if you'd like to have time for questions immediately after your talk. We'll have a longer discussion session at the end of the session. A few of the talks, or I think maybe just one talk we have at the end, is a 2-minute lightning talk, which will present a poster that will be available at the poster session later. We'd like to ask that you keep yourself muted and your video camera off to help with bandwidth unless we call on you. We'll just stick with questions in the chat during the 2-minute chat time at the end. So please preface your questions with a Q and then the person who it's for. And we can go back and touch on any of those that aren't addressed in the longer discussion session. And please just be respectful not to share screenshots of people's work without their permission. Okay, so then I'll hand it off to my co-chair, Pascal Lee, to get started with the first presentation.
Hello, everybody. Thank you, Carolyn, for the introduction. Hello, everybody. So this is an exciting destinations session. The first talk will be by Yuki Kian. The title of the talk, China's Chang'e 5 Landing Site, an Overview. Go ahead, Yuki.
I think you might be muted.
Oh, sorry.
Yes, now we hear you. Excellent.
Yeah, sorry. Hello, everyone. This is Yuqi from China University of Geosciences. And today I'm going to talk about the Chang'e mission landing site. What is Chang'e mission? Chang'e mission is China's first lunar sample return mission. There are two methods used by Chang'e to sample lunar relics. The first method is using a drill to sample the subsurface materials. Another method is using sampler A and sampler B to sample the surface samples. And in total, 1731 grams of lunar samples was taken back to the Earth by the Chang'e 5. Where is the Chang'e mission landing site? The Chang'e mission landing site is in the North Oceanus Specularum to the west of Mare Imbrium, and in the northwest lunar side, the Chang'e landing site is within a Persellarum KIP terrain, which is a geochemical anomaly province with evaluated heat-produced elements are very thin crust. And because of this, maybe the reason why Chang'e landing site developed some of the youngest lunar basalts on the Moon, which I will describe later. And if you take a look at these WAC images and NAC images, you will find that this place is a very ideal place to study lunar mechanism. Most of this region was covered by mare basalts, and there is a huge volcanic complex on the south boundary of the landing region, and there is some other silica-rich domes in the east of the landing region, and there is a very, very long strenuous race crossing the east of the landing region, which I will describe later as well. And if you take a look at the Harry Hinziger's lunar mare age unit map, you will find that the Chang'e landing unit here, it is one of the youngest lunar mare resources on the Moon, and it makes a lot of meaning of the Chang'e mission. And how is this young mare unit like? Based on composition data from WAC and lunar perspective images, we found that this unit is a type of intermediate titanium mare resource. And the thorium and other incompatible elements are evaluated of this young mare resource. And actually, we don't know very well how and why thorium and other incompatible elements evaluated in mare resource. Up to this point, there are two hypotheses. One is the inherent hypothesis, another is extraneous hypothesis. Based on the work of Fu et al. In JJR Planet, they think that the thorium are endogenous to the mare resource here, but I think that is far from well known, and the Chang'e samples will provide lots of information on this point. And I also studied the spectra of over 500 small fresh craters in this region, and using modified Gaussian model to model the relative abundance of different minerals. And I found that clinopyroxene is the most dominant mineral in this region, followed by orthopyroxene and olivines. But if you have read some spectroscopy work based on M-cube data, many authors propose that the olivine should be very rich in the young male units in Oceanus Polaris, but I don't see many olivine of the Chang 5 landing site. And I think that the Chang 5 samples will provide many ground truths of the spec of this kind of young high titanium mineral resource. Are they rich in olivine or not? Other things people care about are the chronology. The Chang 5 young male unit are homogeneous in composition in general, but there are some small composition variations. What do these small composition variations mean? Are they from impedance mixing, geochemical evolution in one flows or separate flows? I want to know how. I want to know more information. So I did this great counting map of this young male unit, and I found some internal age variations within this unit. Actually, this unit has also been dated by many other authors, and we get ages from 1.2 giga-year to 2.1 giga-year. The good news is the results from all authors are within the Eratosthenian approach and younger than all upload and lunar samples. And here is the results from other two authors. They also dated small areas within this unit and get different ages, and also found age variations like me. So what can choose the age variations within this unit? Is this because of continuous eruption or local geology, or the selection of critical counting areas, or the method uncertainties? Or we really need to update the lunar culture function in a young time frame, or rethink about the critical counting methods? I think the Chang 5 samples will provide us lots of precise information of this point as well. And what's the formation? A range of young male resources in this region. There are no other observable eruption sources in this region except Rima Sharp. It's very natural for us to, and the Rima Sharp is very close to the Chang 5 landing site. So it is very natural for us to link these two things together and study their relationships. And here are some numbers of Rima Sharp and Rima Prince. Rima Sharp is much larger than Rima Prince, which was already modeled by Horwitz et al. And they think that the formation of Rima Prince need lavas between 50 to 200 cubic kilometers. And because Rima Sharp is much larger than Rima Prince, it's very natural to extend and think that the formation of Rima Sharp is much more lava than this number. And this lavas must be deposited somewhere in this unit. And this unit has a volume between 1,000 to 2,000 cubic kilometers in volume. And it's possible that this young male unit is just formed by the single eruption of Rima Sharp. And what happens? And we did a detailed work and prove that maybe this young male unit is related to the eruption of SSERVI Rima Sharp here. And here is how. We think that the previous thought Rima Sharp is actually composed of 4 SSERVIs. First erupted Rima Alluvial and Rima Hapalas, followed by Rima Sharp, followed by Rima Marine, and they meet somewhere here in the middle of this unit. And then the materials from Rima Sharp cover all this young male unit. The materials from Rima Sharp cover the southeast corner of this unit. And except for these are images of Chang 5 samples, we will see that the samples are very diverse, including glucinates, breccias, basalts, and glasses. To better understand the samples and maximize the sample meanings, it's better for us to know much better the sample surveillance. Based on the work of Xie et al., myself, Zhao et al., we have made some constant conclusions that the exotic materials here are very minor. Local materials dominate the regular compositions, and the exotic materials are mainly from distal hepatic ejecta, meteorites, and volcanic gases. And because the hepatic ejecta are dominant exotic materials, I traced all of them in North Oceanus Polaris, and I found that the ejecta are mainly from northeast direction, northeast southwest direction, and the overlaying the Chang 5 young male unit and should be the dominant ejecta. And the largest difference between my work and Xie's work is that they think northeast and southwest direction ejecta from Sharp B crater, but I think that they are from Hapalas craters. Direct dating Sharp B crater on Hapalas crater will unreliable ages because the morphology here is very complex. And I think that if you take the morphology here directly, you will find that Hapalas crater looks much younger than Sharp B crater. But if you dating their continued ejecta, the crater count will show you Sharp B crater is younger than Hapalas crater. So I think the critical counting here will impeded by different failures like self-segment craters, partial barrier craters, abnormal degradations, etc. But because this northeast southwest direction ejecta overlaying all this unit, and it should be very critical in the Chang 5 sample studies. So I propose that in the future, people should be have more cautions of critical counting on these two craters. And here is a list of my conclusions. It's one of the youngest mirror basalts on the moon, and maybe erupted from Rima Shaft and exotic materials, maybe from Harpalas, Aristotle, Copernicus, volcanic glasses from the south vents of Rima Shaft and Rima Marine. And I propose two calibration points. One is from local mirror basalts, one is from Harpalas crater. Thank you.
Thank you very much. We have over a minute left. Very good timing, Yuki, and great talk. I don't see any questions from the session members yet, or participants, but I have one. What is the mass of the samples that were returned both by the drill and separately by the samplers?
From the drill, the sample mass is like 215 grams. From the surface scooping device, it is 1.5 kilograms. So most of the samples are from the surface scooping device, from sampler A and sampler B, from the very surface of the landing site.
Yep. And what are the largest fragments you brought back? Coherent fragments?
Maybe 2 millimeters, several millimeters, not very large, because it's a robotic arm, cannot sample like centimeters borders, but just millimeter fragments.
Yep. And can you comment on the abundance of agglutinates? Were they similar to what we have at the other Apollo sites?
I don't know this point yet because the sample analysis is ongoing and maybe needs some time to see the publication of the sample results this year. I think the results will come out very soon.
Okay, so we have some good questions here. Do you expect any fragments of highly silicic material in Chang E5 samples from Mahesh Anand?
I think this is possible that there are some silicate or involved composition in the Chang samples, because you see that this is the Chang 5 landing site, and here are some silica-rich domes here. This is marine domes, 1, 2, 3, 4, 5. Sorry, 4 marine domes. They are silica-rich and very close to the landing site. And there are some small impacts on these domes, and the small impacts on these domes can definitely deliver some materials to distance ranges, maybe can sample by Chang 5. And because, yeah.
Okay, Yuki, so I apologize. We need to move on, but we will have more time for you to answer questions in a discussion session. The next talk is by Caroline van der Bogert, Ages of Geological Units in the Schrödinger Basin Context for PRISM CLIPS 2024. Okay. Go ahead, Caroline.
Get my screens sorted here. And I just realized I should probably choose a different background for myself.
Yep, I don't have a timer background
for everybody. I'll just start the timer. I've got the timer on my PowerPoint, so I can go off of that and stay on time. I promise. So of course here now we've ended up on the wrong slide. Okay, so let's get going here. I wanted to, in the scope of, because of the PRISM CLIP selections, to have a look at the ages of geologic units in the Schrödinger Basin to give a context for whatever mission was selected, or missions were selected, or instrument packages were selected to be delivered there. And so let's just really quickly look at the background, because of course I needed to go back and look and see what do we already know. We know that Schrödinger is the second youngest basin, lunar basin. It had originally been mapped as being late Nectarian by Wilhelms 1979. But he later observed some the fact that there aren't any superimposed Nectarian aged craters, and basically moved it then to be between the Imbrium and Oriental basins. So that moves it into the Imbrium period. Kurlan et al. on the large SPA map that she presented at a poster yesterday also places it into the lower Imbrium due to its morphological characteristics. So we have various geologic units in the basin that we also would like to know something about the age of. The basin materials, there are some light plains unit, the sort of purplish or this pinkish unit that's mapped here. Dark plains, very small little bits of what are mare patches that were observed now later than in this original mapping by Wilhelms. There are naturally the dark mantle deposits, the vent materials that everyone is very interested in. And there are overlying Eratosthenian crater materials, as well as possible secondaries from the Oriental Basin. So what do we know about the absolute age of the Schrödinger Basin? Well, MEST had a look at crater size frequency distributions using the Hartmann chronologies and suggested that the basin might be Nectarian based on the fact that it exceeded the Imbrium chronology line in his plot at the smaller crater diameters. But the craters that are larger than this actually are below the Imbrium line. I miswrote that here. And so basically, I think the interpretation here is maybe that here probably we have an effect of secondaries from the Oriental Basin, and this could push the age determined for the younger craters to a somewhat older age. Also, we have work from Neukum and from Orgel et al. Orgel et al. Worked on the data set that was generated by Fassett et al. In 2012 and basically fit ages both cumulatively and differentially using a new correction. And she gets 3.86 billion years, and that's consistent with what Neukum got for an age of the crater. Now you notice as we continue on in a few slides with adding ages that I have added a little timeline in the upper corner. You can follow along the sequence of events. So, but first I want to review what do we know about the ages of these units. And so what do we know about the dark mantle material? Well, Shoemaker et al. In 1994 looked at the area using some high resolution Clementine data and basically interpreted it as being as young as Copernican, so anywhere from 2 to less than 1 billion years old, based on observation of the crater diameters that were in equilibrium. Okay, and then comparing that with other work to get an estimated age. MEST also looked at this area and estimated an age of 3.2 to 2.5 billion years, using Hartmann's chronology in the same form as that figure that I showed earlier, and comparing this to the relative ages of the different units. So that's what we know previously about the dark mantle. The light plains had been measured with a crater size frequency distribution in 2013 for a study of light plains units to get at the origin of light plains. That's this red area that's marked here in this map. And the dark plains were also looked at in the MEST and Shoemaker works as being mid-early to late Imbrium, or about 3.2 billion years in the same, using the same estimation techniques. So what we wanted to do now was to look at these units all using one technique. We wanted to use the Neukum et al. Chronology and update the existing Hiesinger measurement because we have access to that CSFD, of course. And then we wanted to do new measurements on the dark mantle deposit as well as the dark plains materials. And so these are our count areas that we are using for this study. And these are constrained, for example, based on image availability and wanting to have consistent illumination angles, etc. Okay, so what are our results? When we update the light plains age from the Hiesinger et al. Data set, we get an age of 3.81 billion years. And this CSFD is well fit with one lunar, with one isochron of the production function, which suggests that this is one discrete event. Then we looked at the dark mantle deposit using TC data to look at the northwest flank of the vent, and we determined an age of 3.7 billion years. Then looking at the dark plains, this was rather difficult because some of the little patches gave us CSFDs that could not be fit with an age, and others exhibited equilibrium, like this one that I plotted here. But what we can say from this plot is that because the equilibrium condition extends to larger crater diameters than the age that can be fit for the pyroclastic deposit, that this Mare deposit is likely older than the pyroclastic deposit. So we can at least get a relative age for that. So out of this compilation of data and our new measurements, we're able to give a formation sequence where the basin forms first, the deposition of the light plains happens, the Mare happens sometime in between the light plains and the dark mantle deposit, and that was all wrapped up by about 3.7 billion years. So to say a little bit more about the interpretation of the light plains, what are their origin? I mentioned that the CSFD is well constrained, and so this indicates a single discrete origin. It postdates the Imbrium basin. It's somewhat too young to really be considered as Schrödinger and Breccia deposits, and so this is actually seems to be consistent with materials delivered by the Formation Orientale, which also has an age of 3.81 from the Orgel data set. And this would also be consistent with the stratigraphic relationships in some of the geologic maps. What can we say about the dark plains and the Mare deposits? Well, they superpose the light plains deposits. And as I mentioned, they're in equilibrium at larger crater diameters than we can fit the vent CSFD. And so they're going to be older than pyroclastics. And so this is a bit older than the MEST interpretation. And then finally, the dark mantle deposits, our result is giving an age that's much older than these previous results. The MEST data set, however, only measured 19 craters, and our data set contains 69 that are actually fit, and many more craters in the smaller diameters. And the Shoemaker work didn't actually use a lunar chronology to fit their data. So I think that we can be confident that we have a pretty robust new age. Now, given the time, I just wanted to very briefly mention that we had also done measurements in the Apollo 17 area to compare the whether we could actually measure a CSFD on pyroclastic deposits that would give us an age that's consistent with the radiometric age of the orange glasses collected there. And indeed, we could do this. And so we feel that this previous study supports our ability to get a robust age for the vent. And this points to all of the units in the Schrödinger basin having formed in the Imbrium period. And this, of course, then has implications for the cold traps and the ages of the cold traps where you might find volatiles that were erupted at this location. So thank you very much.
Thank you. Thank you, Carolyn. Excellent talk. In fact, I'm going to update my talk in real time based on your information. You are just at the 10-minute mark here, so let's move on to the next talk. And again, we'll have discussions at the very end for everybody, and also some the chat box is running as well. So the next speaker is Samantha Bell, and the title of her talk, Geologic Map of a Segment of the Schrödinger Peak Ring and Potential Rover Traverses.
Can everybody see the right screen?
Yes, we do.
Yeah, great, perfect. Thank you very much. I'm presenting on behalf of a group of exploration science summer interns. Did an internship at the LPI in 2018, where we produced a map of an area of the Schrödinger basin. So as you can see from this diagram, we're looking here at the moon from the South Pole, and the Schrödinger basin's highlighted there in yellow. It's found within the SPA basin, and it's a high priority site for future missions because a lot of the objectives identified by the National Research Council in 2017 can be accomplished at this location compared to other sites on the moon. So in terms of Schrödinger itself, so it's 320 kilometers diameter and it has this 150 kilometer peak ring structure. So the peak ring, as you can see here, if I just turn this on to laser pointer, peak ring structure is here. And previous mapping in the Schrödinger basin identified different lithologies using M-cube data. So there's mineralogical signatures of anorthositic material, peroxine-bearing anorthositic material, noritic and troglodytic. So very important lithologies within the lunar crust. So previous mapping has been on quite a detailed level of scale. So looking at individual outcrops and looking at this M-cube data to see what we can find in the peak ring. And models have suggested that the troglodytic material potentially could have been uplifted from 15 to 26 kilometers from within the lunar crust. So it's got the potential to answer lots of important lunar questions from looking at this peak ring material. So this is where our project came in. We decided to take a closer look in detail at like outcrop scale and map a larger portion of this peak ring material, what we deemed as the southwest peak ring, to see if we can identify the geology there and to possibly develop rover traverses. So the data sets that we used included lunar reconnaissance, orbiter images, primarily, but we also combined it with several different data sets, including, as I've already mentioned, the moon mineralogy mapper data. And for the traverses, we obviously had to consider things like slope and elevation as well. So for the geological mapping, we mapped over 15,000 separate shapefile features, and these included, as shown in A, outcrops, and we tried to match these with M-cube data to get an idea of the mineralogical signature of these areas. And we've also got, we mapped craters, 190 fresh craters in the area. In C, we've also got an example here of some of the faults and the grabens that were cross-cutting the peak ring. And in D, we mapped the edge of the talus material, so sort of the boundary of the material that's coming off this peak ring. So this is the geological map that we produced. So we took it a step further, mapped the outcrops, and then we tried to consider such things such as changes in slope to try and put boundaries on different lithologies within this peak ring area. So some of the lithologies to sort of draw your attention to this inferred troglodytic in green. We do have also areas which were what we call investigated unknowns, where we just didn't have enough data to confidently assign that to a particular mineralogy. So in terms of geological interpretations, these are just a few that we wanted to highlight in this talk. So we found that faults, excluding the grabens, were radially orientated with respect to the centre of the basin, which could hint that there's more complexities within the way that the peak ring was formed, and possible rotation of fault blocks or interaction with underlying topography that meant that they're not sort of as concentric as you might theorise. And when we were looking at the lithologies, we also considered whether they were in magmatic contact with each other or faulted contacts. So we saw evidence of both, as you can see highlighted in this upper zoomed in portion of label number 5. We've got troglodytic in green in magmatic contact with an anorthositic material. There was not a change in slope that would indicate that this was a faulted contact, which obviously can tell us things about processes within the lunar crust and lunar crystal formation. And we also did, on the other hand, have faulted contacts. So this can tell us about how the peak ring formation process and how material comes to be juxtaposed against each other. So overall, without going into all the details, we did find, we did find enough reason that this area is particularly geological interesting and would warrant sample return mission, could answer a lot of high priority science goals. So that led us on to planning some different rover traverses in the area. So we had, just to get your eye back in, this is the area that we mapped, shown here in the white square. Zoomed in, we then zoomed in even further into one small area that we targeted. It had to obviously be a combination of somewhere where the rover could land, as much as we'd like to go into this peak material, right up into the peak ring material, it's just not safe, and capture enough of the different geology and the complexity in this area. So we planned a human-assisted robotic sample return traverse mission on a 14-day timeline using an Orion or Gateway element or a modified Heracles architecture. So this is the proposed traverses. We did 3 traverses in the end because there was lots of different sites that we wanted to visit, and working out the best combination inevitably meant that certain things were left out of some traverses compared to others. So this was done sort of as an example of some of the trade-offs that they maybe need to think about in these areas. Traverse A, just to get your eye in, is in white. All had the same landing site and endpoint. And Traverse A was designed to maximise the diversity of samples, so not as many stations along the way in between some of the key sites. In comparison, Traverse B, shown in purple, was designed to do more in situ analysis at each station, so I'd spend longer at each station and therefore couldn't traverse as far. And samples, Traverse C, focused in red here on collecting different samples from the different mineralogies identified by this overlay and M-cube data here, and the contacts between each of the morphologies. So overall, the scientific potential of any one of these possible traverse routes was quite high. So we could potentially sample from outcrops of material that we've got some signatures of with the M-cube data. We can image cross-cutting faults. So just to get your eye in here, this is sort of the edge of one of the grabens.
2 minutes.
Thank you. And we could also potentially collect Schrödinger impact melt exposed from some of these fresh craters like this one on the left. And I'm sorry, these slides keep jumping. And sample lots of different peak ring lithologies, so the anorthositic, noritic, troxylitic mineralogies. And this would serve as ground truthing for M-cube data and allow us to potentially investigate that magmatic versus structural contacts that we identified in our mapping work. So this is just the summary. So we created this geological map of this southwest peak ring area, the Schrödinger Basin, revealed lots of complex geology that we designed 3 potential 14-day traverses for, and it has the potential in this area to address numerous high priority science goals. For further information on the traverse or the map, please do check out our paper that we published in Planetary Science Journal for any extra information. Thank you.
Thank you very much, Sam. Excellent talk as well. We have a minute or less for a few questions for you. I'm not seeing anything in the chat box this minute. So I was going to ask you, you propose 3 potential 14-day traverses. Do you have a favorite one, and sort of why, if you had to do only one of the 3?
I think each has sort of had a different favorite one, yeah, the idea would be that it was sort of just to illustrate that you could tailor that particular area to really highlight different things. If you were going to collect all the peak ring morphologies, then Traverse C would be your option. But if it's maybe your first time there, Traverse A could be a good option to get an idea of everything. So yeah, it was a learning curve for us as well, the trade-off between what we would like to do and what we'd maybe be able to do in the time scales. Okay, great. So with the 0 time mark, Sam, you have another question in the chat box, so you can maybe respond there. Cool. I'll hand it over to Carolyn now.
Great. Now it's my pleasure to introduce my co-chair for another talk about Schrödinger, this time Schrödinger Cat, a proposed NASA PRISM investigation of the vent and the permanently shadowed regions that are in the basin.
Thank you. So this is a failed NASA PRISM proposal, although we actually felt that based on the reviews we received that it got pretty close. So It is my pleasure to present the work of a large team of people. The organizations represented are the SETI Institute, where I'm headquartered, along with Doug Caldwell, who would have been our project manager. Ceres Robotics for the little rover device that would have deployed our 3 instruments. The 3 instruments would have come from one from Ceres Robotics, the 2 others from NASA Ames. We also have researchers from NASA Glenn, JPL, Johns Hopkins, APL, Carnegie Mellon University, the Lunar and Planetary Institute, Planetary Science Institute, Western Carolina University, and Max Planck Institute for Solar System Research. So Schrödinger Basin, I don't need to introduce that again to you, but the key thing to note is that, of course, it's straddling here the outer zone of the South Pole Aitken Basin, and being one of the youngest impact basins, Schrödinger Basin, it likely has exposed in its surface materials, materials that would have come from the upper mantle of the moon via the South Pole Aitken Basin, which preceded it. The basin itself has many features, as we've seen this morning, but the mission that we were proposing, the deployment of our 3 instruments, it's a mobile instrument suite that we proposed, would have gone and focused on the pyroclastic deposit, also known as the dark mantle unit of Caroline, in this Schrödinger Basin. So the scale bar is shown here at the lower left. It's 20 kilometers. So this is a large, massive pyroclastic deposit on the floor of Schrödinger Basin. So this is a mosaic of the Schrödinger pyroclastic deposit, showing you in more detail the Schrödinger vent, which we acronym as SV in the rest of our talk here. The pyroclastic deposit is about 415 meters tall, rising above the floor of the Schrödinger Basin. It's about 35 kilometers wide, and according to Caroline, it's now 3.7 billion years old. Before that, it was estimated at ranging from 1 billion or so, at least Copernican in age from Shoemaker, to maybe 3.1, 3.2 by Mest. So this is a closer up of the Schrödinger vent. North is now to the lower right. And there are a number of interesting features about this vent. One is that there's actually a relatively shallow ramp that is very inviting in the southern side of it. So at the top of the image, if you are at the sort of the crest of the vent on top of the Schrödinger of the pyroclastic deposit, you have a gentle ramp taking you down into this vent. The maximum slopes of order 17 degrees, which are even less than what the lunar rover drove up and down on Apollo 17, for example. Inside this vent, there is a small impact structure. I mean, the largest, there are actually several impact structures, but the largest one is a relatively small one. It's about 200 meters across, and that's a crater that we named the De Broglie crater, sort of provisionally. And of interest as well are these high albedo outcrops, which are found at sort of mid-height, mid-elevation inside the vent. And the vent itself presents a permanently shadowed region in its northern end, which is of course very exciting, because now we are looking at the possibility that it be cold trapping not only exogenous volatiles, but potentially endogenous volatiles as well, associated with the volcanic activity at this place. Now, we don't think that there would be exposed volatiles at the surface because of the indirect lighting from the rest of the vent onto the PSR. So the PSR might not be completely dark and therefore not extremely cold as the ones at the poles. But at the same time, the subsurface, we would expect, might be able to hold a concentration of volatiles in the PSR. So this is a profile of, well, this is a perspective view, but in the insert set, you see a profile, A to B, that's shown at the bottom of the image. What you see here is that the pyroclastic deposit rises above the floor of Schrödinger Basin, drops down again towards the southeast, and the vent itself is relatively deep because it dips below the level of the floor of the Schrodinger basin. And what's interesting is that the outcrops that I was pointing out earlier, according to one of our co-investigators, David Kring, the outcrops could be either a carapace of volcanic melt exposed here on the sides of the vent. It could be potentially distal impact ejecta from nearby highlands. But more likely and very intriguingly, it could be exposed bedrock from the Schrodinger basin floor because of the elevation at which it appears, and also some hints of layering that we see in these outcrops. And below these outcrops, there are rock falls that would allow you to examine up close samples that presumably would have come from these outcrops. And so the mission that we were proposing was to go investigate this pyroclastic vent, but also, and of course, its PSRs and volatiles, but also the potentially extremely fresh Schrodinger basin floor material that are still preserved and might have rolled down from these outcrops. So the hypotheses we were going to test, here's a subset of them, that the pyroclastics at Schrodinger vent are compositionally distinct from the Apollo 15 and 17 glasses, which would imply that there's substantial lunar crustolateral compositional heterogeneities. The PSRs, large and small, I just mentioned the large one, but even the Broglie crater has a small PSR. These PSRs at the Schrodinger vent are associated with volatile concentrations, once again, not at the surface, but presumably in the shallow underground. That the volatiles would include both exogenous and endogenous volatiles. That otherwise, at least 100 ppms of water might be present even in sunlit areas. This is because this is a high latitude site, and we're building on the observations reported by recently by I forget her name. It'll come back later. The Sophia detection of water in at 400 ppm levels in Clavius crater is what I was referring to. The high albedo outcrops in Schrodinger vent are Schrodinger basin impact type, so that's the hypothesis we would like to test. Also, with our imaging system, we could examine electrostatic dust levitation, and that this process is active in the highly shadowed sort of landscape of this high latitude site. And regolith mechanics would also be examined to determine how humans might eventually access this location for scientific exploration, of course, but also for ASRU. So there were three objectives to our mission: characterize geologic features, characterize the composition of surface materials, characterize their mechanical properties, and how materials move. Three instruments, an imaging system on the rover, including 2 cameras on a pan and tilt platform, the NERVIS instrument, which is already on Viper. We would have reflown that same instrument spectrometer for compositional analysis, but also for temperature measurements, and a neutron spectrometer for bulk composition and hydrogen detection as well. So the event shows up as a thermal neutron anomaly that's relatively low.
1 minute.
Our instrument would have been able to identify different types of glasses. This is the statistical uncertainty that it would have presented as shown in the upper left. And here is a traverse, a notional traverse that we have put together to explore this vent. Of course, you have to work around the shifting lit side of the valley as you drive down, so that you're always in lit terrain. So this is showing us how we would have landed on the edge of the vent and driven down over the course of 8 days to the bottom of the pit. And I'll just end with some nice views that we were planning on getting had we been selected and flown. And so this is a depiction of our little rover carrying its instruments going down into the Broglie crater. All right, thank you very much. This is it.
Okay, thank you, Pascal, for the really interesting description of important things we still need to know and that we could investigate at Schrodinger using a mission. So maybe we just need to get more missions proposed for these geological things.
We should talk, Carolyn.
Definitely, definitely. So we need to then move on to the next talk, but please do put any questions for Pascal into the chat, and we can come back and discuss Schrodinger at great length during the discussion. So Harry is putting up his slides, and so I will introduce him. We're returning to the near side now, and Harry is going to talk to us about the Rima Bode region as a new landing site, exploration site. Take it away, Harry. You're showing, do the switch your, yeah. And you're still muted. Harry, you're muted.
Okay.
Excellent.
All right. So today I would like to share some thoughts, preliminary thoughts on the Rima Bode region that might be actually an interesting site for studying volcanism on the moon, and also as a potential ISRU site. And obviously I'm presenting on behalf of many different people here that I list on the slide here. So what was the motivation and the framework? Well, a couple of months ago, a year ago, ESA issued a call that asked to think about how ESA's large lunar lander can be used for science and research, basically. And that was, of course, in the larger framework of the increased and great interest in returning to the moon by many spacefaring nations. And so we were thinking of basically using this EL3 lander to touch down on the surface and then have a rover basically extending the area of research that can be covered. In an ideal case, this rover would have some night survival capability. It could be operated by humans from the gateway or from Earth. That's still up for decisions. And right now, as is my understanding, that the first EL3 lander will not be sort of targeted to return samples, but one of the next ones will be. So for the moment, we were planning for some in situ observations with the option of sample return. And compared to all the landing sites on the far side and the polar areas, we were thinking of a simple landing site because ESA has never soft landed on the moon so far. Nevertheless, it should have some high scientific potential and basically should help answering multiple questions. And so that limited our search for the near site, where we have direct communication, and of course the site should be safe. Nevertheless, should have some potential for some excellent science in various fields. And we picked the Rima Bode area, and I just want to point out that this is of course nothing specifically new. The Rima Bode constellation site is actually just to the northeast of our landing site, and that site was described by Spudis and Richard in great detail in 2018. So just to orient yourself, so we are looking at the near side, central near side, so we're at about 11 degrees north and about 5 degrees west, just southeast of the Imbrium Basin. You see the rim structure and sort of situated in between Mare Volporum and Sinus Estum. So the red box is the area of interest. And right away, you can see that this is a particularly interesting site because Copernicus crater is close by, Eratosthenes crater is close by, and the Imbrium is close by. So 3 of the chronostratigraphic time markers are basically contributing material to this particular site. And in addition to that, you see the very, very dark area here, the very low albedo, which was interpreted by Geddes and also by Spudis to consist of glassy material, pyroclastic material, dark titanium-rich glass beads, basically. So when we zoom into this area here now, This is the site of interest, and right away you can see that the area is indeed very special because you have this mantling deposit of the pyroclastics on top of some more highland material. You see a beautiful wrinkle ridge that is close by to the east, to the west, and you have a fairly fresh impact crater, Bodhi also in this area. In addition, of course, you have Rima Bodhi that you can see on the lower right of the image. So if you look into this area, I can see many different things that are interesting. So particularly at one site, the one, we could get access to these pyroclastic deposits. We could drive up this ramp basically and collect material. We have in site 2, we have this fairly fresh impact crater, very blocky, that would give us access to boulders, but it would also allow us to have a pretty good look at this crater wall. At site 3, we have again pyroclastic deposits, but if you look into the composition of these pyroclastic deposits, they appear to be somewhat different at site than the pyroclastics at point 1. At point 4, you see this dome-like structure or cone-like structure, which might well be a volcanic vent. So that's something that is a hypothesis to be tested. At point 5, you could have access to some highland material. At point 6, you see that Copernicus ray material is basically extending towards the east, and so you could sample the Copernicus material there. At point 7, you have access to some unmodified basalts, if you will. And then at site 8, you could cross actually the wrinkle ridge, and with a ground penetrating radar, you can get the structure of there, but you can also sample some Eratosthenes material. I called it ray material here, but what I really mean is that Eratosthenes contributed material from that direction. And then, of course, at point 9, you can drive across the ejecta blanket of Bodhi crater, and you would get the very nice profile of the underlying substrate, basically, that has been ejected. And so Bodhi serving as a drill hole would basically be then reflected in the deposition of the ejecta blanket and the composition of the ejecta blanket. So those are a couple of things that I think make this area very interesting. Now, how can you do this? Well, I just put in our landing site sort of in the center somewhat, and then you can see individual traverses to these sites. I also show the distance to the endpoint. So these are all numbers that are fairly within reach, nothing special that we haven't done yet. So I just remind everybody that Lunar Cod 2 drove about 39 kilometers and it took about 5 months. Okay, so I think we can do actually faster and better. But on the way, of course, to these final points, you have different stops. So the traverses were planned to basically stop by at individual craters to get information from that. So all the yellow data points are related to impact craters. The ones down here are related to some highland material that can be sampled, and the green ones are basically different volcanic materials that can be sampled. And finally, up here, this one and this one are related to tectonic features. So this is basically sort of the outline, what you can do, what is the rationale and the thinking about all this. Well, for each landing site, for each point, basically, we have a long list of questions that we would like to answer. Of course, you can also do this in a loop. So if you do that, it would be about 180 kilometers. So it takes you about 22 months if you do that. And so here are just a couple of examples of what the interesting things are. So this is the vent. Basically, you see different impact craters that allow us to study the regular structure. This crater here is sort of covered partially with vent material. You see this layering or mass wasting features here. If you go up to the wrinkle ridge, you see again an impact crater with a very unusual central ridge, very young craters, very blocky craters up there. So that's interesting. And then the Bodhi crater rim itself has a very nice small crater that excavated very, very large blocks. And we can also see different blocks in material in this area. if you look at the color ratio composite, you see differences. So it's not a homogeneous unit. And when you zoom in, for example, if you look at Miriam's work, this area is not particularly rich in plagioclase, but nevertheless, we see differences between these mountains and the mountains down here. So that's somewhere where you can access plagioclase-rich material. Also, the basalts are different in their clinopyroxene composition, and of course, the pyroclastics are also different from the basalts. If you look at the titanium concentration, you see that we have access to high titanium pyroclastics that are actually different between 1 and 3. So that's interesting. And of course, any landing site that has to fulfill the science has also be a safe landing site. So we are landing on this bench basically into semester. And so if you look at the slopes, fairly benign slopes. So even if you drive up to the rim of Bodensee, you are less than 10 degrees. And also you don't have to worry too much about rock abundance. On the other hand, you can access rocky material in many places. And that brings me to my conclusions that you can read, and I take your questions. Thank you very much.
Okay, thank you, Harry, for a very interesting discussion or presentation of a lot of really interesting things that we can look at around the Rima Bode area. We do need to move on to the next talk, but Harry, there's a couple questions in the chat for you, and then we can also come back and discuss more during the discussion period. So I'd like to then introduce the next talk. Sasha Mikolayevsky, and he's going to talk about a landing site evaluation of the Moscoviense Basin. Sasha, you can go ahead and share your slides.
I started screen sharing and hope you can see it. I will
start the clock.
Goody. So let's plunge into the Sea of Moscow. I present to you Mare Moscoviense candidate landing sites. So first of all, Mare Moscoviense is one of the few maria we have on the far side. So it would be interesting to investigate it there. So we have no samples from either lunar far side or the lunar poles. And if we get our hands on new samples, that could lead to insights into the timing and the evolution of far side volcanism, and also into cratering processes from the lunar far side. The few sample sites we have on the moon are all located in a small region. And as you can see in the image on the right side, all of them are on the near side, except the yellow dot on the far side, that is the Changi 4 landing site. Here they investigated the soil, lunar soil with remote sensing techniques. So where is Mare Moscoviense located? It is located on the northern hemisphere of the lunar far side at around 22 degrees from the equator and at 140 degrees east. And as you can see, it is one of the largest maria on the lunar far side. We have here, down here, the South Polaitkin Basin, and here a Tsiolkovsky crater. And so where are our landing sites located? So here's a quick overview. Our first landing site is here, Red Star, located north of crater Titov. The next landing site is Yellow Star, a bit north from the larger impact structure here, crater Komarov. West of Yellow Star is the landing site Blue Star, located on darker Mare material. And the last landing site is west from Blue Star, located between two floor fractured craters. It is here, the landing site Green Star. So part of my master's thesis was to look and to examine the region and come up with a geological map of the study area. So here is part of my master's thesis, a geological map for the area. We have Red Star located on two Mare units, an old and an old Imbrian and a younger Eratostinian. We have here Yellow Star located on an Imbrian unit. Blue star also located on the Eratosthenian and Imbrium unit, and we have green star between the two floor fractured craters with a bit younger age compared to EMM1. So let's dive into the landing sites. We start with the 4 landing sites. I give you a quick overview in a neck images, and then I move on with digital elevation models, slope maps, and the rock abundance map for each landing site. So first of all, we start with red star. As you can see, the landing site is relatively flat, a smooth surface. We have the inner circle is a 1 kilometer radius where we could land with a lander. The outer 3 circles are at 5, 10, and 15 kilometer radius, which could be the operating radius for an upcoming mission on the lunar far side. The largest crater on this landing site is located in the southern part. Here, they are approximately ranging between 500 meters and up to 1 kilometer. Material which could be sampled here is ray material from a crater located east from the landing site. And we could also sample here some younger, fresher craters. So in the elevation model, you can see that the area is relatively flat, a smooth surface, which would be good for safely landing there. And in the slope map, you see that the area is kind of not steep inclined, which would be also good for landing there. The threshold angle for safely landing is between 10 and 12 degrees. So most of the area fulfills that. Only at the larger craters, the angle increases. And the rock abundance shows that this landing site is mostly covered with blocky material, but nevertheless, it would be also interesting to sample this material and to investigate it. Next landing site is Yellow Star. We have in the northern part of the landing site the rims of two embayed craters. We have here a kind of a dome-like structure. And also you can see that the albedo is different in some parts of the landing site. The landing site is also relatively flat. And as you can see in the slope map, we have only the steep inclinations at the northern part where the 2 buried craters are, and here at the southern part where the dome-like structure is and where some of the larger craters are located. From the rock abundance map, you can see that most of the site is covered with finer regolith material. Only at the larger craters located here, the material is a bit blockier. So our next landing site is Blue Star. We have here a fresher crater. Also, you can see that the material here is a bit darker compared to the northern part of the landing site, and the northern part of the landing site is also a bit rougher with more smaller impact craters. We have also here some fresher material and also some buried craters which could be investigated. In the digital elevation map, you can see that the area is relatively flat, which would be good for roving there. And in the slope map, you can see here the 2 buried craters, also a buried crater here. The inclination angle for the whole area is relatively good, speaking in regard of rover safety, but we have some smaller craters here with steeper inclined walls, which would be not so good if we come close to them. So the last landing site, in the rock abundance map, you can see that only here at the fresh crater, the material is a bit coarser, and also at some craters here in the north. So it would be interesting to sample here and investigate the rocky material, the excavated material. And the last landing site I'll present to you is a green star located between two floor fractured craters. We have the
2 minutes.
Yeah, thanks. We have the crater wall up here in the northern part and the other crater wall of the other crater here in the southern part. We have also some fresh craters here. The largest craters range from 750 meters up to 1.2 kilometers. And the surface area is also relatively smooth and flat, as you can see here in the digital elevation model. And in the slope map, we have steep angles at the crater walls from the two larger craters at the northern and southern region of the area. We have some steep inclinations here at the craters located in between 5 and 10 kilometer radius. And as you can see in the rock abundance map, area is mostly covered with finer material. We have only some blocky material up here where the larger craters are located. So what have we learned so far? We investigated 4 candidate landing sites inside the Moscoviense Basin. All of them are located on different geological units of various ages. All of them are Maria units of various age. For example, Red Star lies on the boundary between 2 Maria units. We can investigate a younger and an older unit. Yellow Star allows sampling of ejecta from crater Komarov. Blue Star is located on a boundary between 2 Marians. Here we can also investigate a younger and an older unit. Green Star allows the investigation of interaction of melt with floor fractured craters. And to sum things up, samples from the far side could lead to a better understanding of the lunar geological evolution and also increase our knowledge of volcanic and impact activity on the far side. And we have different sample locations inside Mare Moscoviense, Mare basalts like Apollo 11, 15, or 17, basin floor and rough material like Apollo 14, and we could sample younger impact craters. Thanks.
Thank you, Sasha, for the nice talk about Mare Moscoviense. You've got several questions in the chat if you'd like to go ahead and check on those.
Yep.
And then we'll come back to Moscoviense during the discussion. We just have 2 more presentations, and I'll hand it over to Pascal to introduce those last 2.
Am I on, Caroline? You're muted. Okay, so the next speaker is Francesco Sauro. The title of his talk, Moving Forward, the Exploration of the Moon's Subsurface, the Lunar Caves Mission Study at the ESA Concurrent Design Facility, CDF. Go ahead, Francesco.
Just a real quick comment here. Francesco is in the field, so he's providing us a recorded talk. He's hoping to join us for discussion, but if not, please do send him emails if you have questions.
Good morning. This is a talk about a study at the Concurrent Design Facility of the European Space Agency, focused on the exploration of lunar caves. So we know that several pits exist on the moon, especially in the Maria, and this could be really important for accessing the subsurface of the moon and studying, for example, the lava flows, sequences, but especially the subsurface environment for potential utilization in the future. So it's a challenge, it's complicated, and we still do not have a clear idea about the technologies that could be required, which depends also on the objective of this kind of exploration. And the scientific opportunities are several. First of all, from the study of the pit itself, so the study of, for example, of layering of lava flows on the Maria, the evidence of space weathering through paleoregolith, for example, fractures and fragmentation from the regolith to the substrate, and temperature gradients. But also there are several opportunities if there is a cave continuation at the bottom of the pit. It could be a lava tube or other genetic volcanogenic type or related to impact melt, for example. And this could be very interesting for exploration because we do not know anything about these environments. They are completely unknown. We do not know anything about the internal morphologies. Of course, about environmental parameters we can model, but we have to confirm hypotheses about their peculiar environment inside. The presence of secondary deposits, impact dust, secondary minerals, and the fact that these could be really pristine environments compared to what we can achieve on the surface in terms of studies of paleo environments on the moon. So there are several challenges. First of all, we cannot really land safely inside the pit or on the rim, so we need to land in a safe area and then move to the pit. We need to address how to do a safe descent into the pit, avoid, for example, rock falling or regolith avalanches triggered by robotic activities. We need to address the power and communication, navigation, and exploration of the cave, and also the fact that these are very peculiar environment where we can have illuminated areas and other in shadow, very peculiar thermal condition through the evolution of the lunar day. So also the European Space Agency in 2019 started to focus on this kind of study, and we had a challenge, a SysNova challenge, open to academia and different consortia. We had several proposals. 5 of them were selected to study innovative system to explore and document this kind of environment. They have been divided in 3 different mission scenarios. One is a scouting geophysical mission where we had a study of a gravimeter and a rover, gravimetry rover by Canadensis trying to detect the cave continuation below the surface, but also smart solution like hoppers developed by the University of Manchester, trying to get a first sight inside the pit itself and try to understand with a quick mission how is the environment within the pit itself for future exploration. The second scenario is already more complete exploration. We have incremental exploration, controlled descent into the pit through a rover platform equipped with a crane. The crane can lower down different cave units, in this case Daedalus, which is, we will talk about it later, but it's a robotic sphere developed by the University of Würzburg, and then a quick preliminary exploration of the potential cave below the bottom of the pit. And the first scenario is a more advanced autonomous exploration mission that is being studied by the FKI from Germany, which is more related to autonomous exploration navigation if there is an important cave continuation below the pit. So the concurrent design facility study afterwards has been focused on two of the system, and specifically in the mission type 2 that had the primary objective of exploring, documenting, and performing scientific observation through the controlled descent to the bottom of the lunar pit, and the secondary objective is to try to explore at least a little bit the cave continuation, the map, document, and understand, of course, the environment. The mission duration that we had as an hypothesis is 1 full lunar day, and we want that to be a near real-time mission with a continuous transfer of information to Earth, and really to achieve the most of science and data that we can achieve during this exploration. So this is just an animation. The study was focused on 2 systems. One is this rover with a kind of stabilization system, and a crane, which has been studied by the University of Oviedo, a scissor crane that can extend up to 20 meters from the rim of the pit and can allow the descent of a cave unit down the pit. And the cave unit that we studied is Daedalus. It's this robotic sphere, completely sealed. It's an innovative system that allows to have spectral cameras, very, very wide angle spectral cameras, but also laser scanning, and can work both during the controlled descent attached to the cable that provides also power, so can really provide a very high resolution 3D model of the pit, and also can be detached afterwards from the cable, and can use a very peculiar type of locomotion through center of mass movements and some rods that are extended from the sphere itself to overcome obstacles. These are some components. As you can see, there are optical sensors and different lenses that allows spectral studies. Also, the LiDAR is very important because allows with different wavelengths to detect, for example, water ice and so on, and of course some environmental sensor for temperature and radiation. So the concurrent design facility was a quite big effort. Usually this is done in prisons, in ESTEC, but we did it online because of COVID restriction. We had 35 specialists from ESA, 23 from the consortia that have been developing the technology. We had more than 60 hours of discussion, and we focus on all the disciplines required to develop a real mission, like environment, landing operation, mission system architecture, robotics, science instruments, power, communication, thermal. And then we had also a full evaluation of the mission feasibility. There will be a report available in the next few months. So this is the final animation. You see the system, the RoboCrane plus Daedalus that is descending with a thermal shield and performing a scan of the pit. Thank you very much.
Well, thank you, Francesco, who is not here today once again, but this was a great talk. We are just going to move on to the next and final presentation, which is a lightning presentation to be given by Pratik Tripathi. The title of... Hello?
Yes.
Hi, Pratik. So title of your talk is Meteorological Diversity of Von Karman Crater from the Visible and Near-Infrared Imaging Spectrometer Data onboard Chang'e 4 rover. Go ahead, Pratik.
So can you see my screen?
Yes.
Yeah. Okay. So I am Pratik Tripathi from IIT Roorkee, India, and I'm a fourth-year student working on Earth and lunar mineralogy using integrated spectroscopic techniques like Raman, thermal, and VNI. And my topic of poster is mineralogical diversity of Von Karman crater from the VNIS data on board Chang'e River. Here, I just compare VNIS M-cube and the nearest Apollo sites for to show the mineralogical diversity of the very next geologically explored Von Karman crater. So I request all of you to kindly visit my poster. Thank you. Thank you very much.
Wow, that's perfect timing. You actually earned the option of getting a question. Let's see, any question for Pratik? Right, so I guess maybe we should just move on, Carolyn, to the discussion. Why don't you take it from here? You're muted, Carolyn.
Too many windows and buttons everywhere. But yeah, so I made a Mentimeter poll that you can go ahead, and I see some people have already started putting in their opinions about how excited we are about the destinations that we talked about today, and also destinations coming up for PRISM payloads. I can share my screen here so that you can see what's going on. Yeah, okay. Those here. Am I still in this meeting?
Can hear you, Carolyn.
Yes.
Okay,
Carolyn. We lost Carolyn. lost
I'm
Caroline.
coming back, I think.
Hi there.
Trying to. Everything worked fine until now. So I'll just need to share the screen again. So you can see what's going on with the results for our first question. So you guys can go into that link and put in the code. Just go to menti.com and put in the code, and you'll be able to then answer, okay, how excited are you about the things that we've talked about today and other locations that are coming up for PRISM. And then in the meantime, maybe we can open up the chat and have a look and see what other just open the chat again. Windows closed. Okay, I no longer can see the chat. So maybe Pascal can open the chat and have a look to see what questions might.
Yep. So I'll start from the most recent one I see. Ryan Watkins, to everyone, I'd like to write in Gruithuisen domes here. I guess that's for the menti.com input, right? Ryan?
Yep, exactly. I have another Menti activity in a few minutes once people have a chance to go into this one, where you can actually do write-in of 2 locations that we don't have on this spider plot.
Yep.
So stay tuned.
Here's a question for Harry, which is a sort of a follow-up on a chat question that you had about what instrumentation or what rover scenario or strategy you might use to explore the various sites that you have there. So why don't you do this verbally with us right now?
Sure, more than happy. Well, I guess the question is whether we should have the spider-like approach or the loop approach. And so the spider-like approach is probably better if you have no night survivability, and so you're restricted to shorter traverses. So there you could go basically on a shorter distance and bring maybe back samples for if the Rima-Bode site is one of the later ones, where you have sample return. So that could be an option. I mean, you could also move the landing site, of course, towards specific targets of interest. If you're more interested in the Wrinkle Ridge traverse, then of course you would land closer there and so forth. And in terms of instruments, I think cameras are obviously the most important thing, but also some spectrometers and some elemental chemistry instruments. So that would be something. And if you are interested in the ISRU, you need to bring some oven or have a laser that basically evaporates the material, the pyroclastic, so that could be an option. And in terms of the physical properties, you could just look at the wheel, for example, how deeply it sinks in to get an idea of the porosity of the regolith and so forth. And also remember, it's not all about the rover. You could have a very capable lander itself, because it's a 1.5 ton lander, and so you can have a very comprehensive geophysical suite of instruments that remain on the lander and stay there for an extended period of time. So,
yeah, very good, very good. And before I forget, I also just received a message from Greg Schmidt to everyone. They will be playing Ryan Watkins's video that we didn't have time for during the STEM Mothers presentation. This video will be played during the break in the plenary session at 9:15. Okay, so this is the video from Ryan Watkins we didn't get a chance to watch earlier. Okay, let's see. Do we have another question? Ryan Watkins' video, will be sharing the video. Breaking the Maternal Wall in STEM is the title of the video, I think. All right.
Okay, so I'm going to go ahead and change the Mentimeter to the next interaction, where you can type in 2 destinations that were not on the spider plot.
Okay.
And then we can continue with discussing any of the other questions that were in the chat.
Okay, any other? We still have 70 participants here, so Any other questions for our speakers or just topics to discuss? Okay.
I'm seeing that just already in the word cloud that we're getting, I mean, five respondents really like Rutile domes or Sarkis Plateau. It seems like there's a big focus on volcanic materials. Now we're seeing silicic domes and Marius Hills as well, Compton Velkovich. So it's clear, I think, despite, we have a number of landing sites that have been selected for different regions and or for different reasons, but volcanic evolution of the moon is still a super important topic.
Yep. And of course, the Gruithuism domes are a target for the next PRISM call, as most of you probably know. Okay, I'm seeing a question here from Hillary Downs. Is anyone thinking about a mission that would collect some olivine-rich material that might be from the lunar mantle? It's well, part of the holy grail, of course, of why we're so interested in the South Polacan Basin, for example. But
yeah, I was just going to jump in and say that. I mean, going to the Olivine Hills area, the center part of the SPA Basin, one of the goals there would be to collect mantle material.
So responses from, but those of you who are responding by chat, we can talk. You can unmute your mics and chime in verbally at this point. So David Kring, for example, responds, perhaps there is a mantle xenolith in the Schrödinger pyroclastic vent and nearby Mare. Yes, that would be very exciting to find. Anything that takes us to the Schrödinger pyroclastic vent is exciting to me, for one thing.
Okay, Hillary is saying not mantle xenoliths, but olivine material excavated by impact. So I guess there we would need to look at remote sensing detections of olivine materials in central peaks of impact craters and things like that, and we just need to plan in visiting one of those locations on a traverse.
Okay, another question. So once again, feel free to unmute and ask or raise your hand, or there's a raise your hand option under reactions at the bottom of your Zoom screen menu.
Now I know we had a lot of questions for Yuki about the Chang'e 5 sample return, and Yuki is just mentioning in the chat that the Chang'e 6 will sample the SPA in 2024, and that mantle material is one of the most interesting targets there.
Yep. Actually, I'm glad you bring this up, Yuki. I think there was a question that would be of interest to everyone to discuss is there a process to work on samples from the Chang'e 5 mission if one is outside of China?
Currently, as far as I know, currently, if international scientists want to work on the samples, you can join the Chinese team. And SINSA has, according to the SINSA's Chang'e 5 sample policies, the samples will be available to scientists outside China. Finally, the question is when they start to receive proposals from scientists outside China. And in a media conference, the same media conference that SINSA delivered the samples to Chinese scientists, they said that they are formulating the rules and details of the sample application for scientists outside China, but this kind of policies and rules should be approved by the government. After that, they will release the details and you will know. And I think someone will put this in the lunar list or in the social media, and you will know how you can apply the samples. And as far as I know, this is the Chang'e 5 sample application run every 3 months, and next time is September. I think, as far as I know, I think it's a December one. and scientists outside China can apply the samples, and we will see actually, and I think the rules will be released very soon.
Yep. I mean, I personally don't do sample analysis, but is there a website where one would find these applications, or are you saying that they're not quite ready yet?
There is a Chinese website, and I can put this in the link, and Google Translation can tell you very well the meanings, thanks to Google. And as far as I know, the engineering team, the programmer are preparing an English website as well, and I think will come together with the start of things are receiving international applications of the sample.
Mm-hmm. Okay, thank you. Yeah, thank you.
It's
Okay.
very exciting times.
Yes. Yes.
Okay, well, if there are no other burning questions for us to discuss right now, I would suggest that we close the session so that everybody can take a break before the video is played at quarter after, the one from Ryan Watkins. And I'd like to thank my co-chair for helping me host a very interesting session. I'm glad that you were all here. And I'd also like to thank Ashkan for doing an excellent job of guiding us through the technology and also taking care of Chesko's talk since he couldn't be here. And so we look forward to seeing you in the poster sessions and in the next parallel sessions later on.
Thanks, everybody.
The recording has stopped.
Probably I can start the session now.
This meeting is being recorded.
Right. So, yes, welcome to the session of Geology and Geophysics. My name is Bajia Iqbal, and I work at University of Münster in Germany. And together with me is Jacob Richardson, and Jacob works at NASA Goddard Space Flight Center. So before we start session, I just have few reminders. So so first of all, your talk is for 10 minutes. 8 minutes are your presentation, and 2 minutes are for question and answer. And you can pin one of our windows, either Jacob or my window, and you can see a timer running next to your presentation. So if we are not able to cover any questions during your 10-minute talk, then we will have a longer discussion period in the end anyway. And I request most of the participants to please stay muted and keep your video's camera off until you're asked by me or Jacob. And yes, you can use chat to ask questions, and when you ask questions, please put the Q in brackets. And we also request all participants to please not to share screenshot or any results of any presenter without their consent. So with this, we can start our session. So first, our first speaker is Sarah Gutierrez, and Sarah, I will stop sharing my screen so you can share.
Great, thank you.
And Sarah will talk about consequences of the nucleation barrier on lunar core formation.
All right, is the timer ready? Yeah?
Yes, I will just put it on.
Awesome.
Right.
Hi, everybody. I'm Sarah Gutierrez. I'm a graduate student at Case Western Reserve, and this is my work I've been doing with the guidance of my advisor, Steve Hauk. Today, I'm going to tell you why the nucleation barrier is really important for the moon's core history and further compel new sample collection and more seismometers on the moon, as they would strengthen our models for dynamo theory and planet evolution. Okay. In the largest picture possible, this work is about understanding the great diversity of magnetic fields in our solar system. Why do Ganymede, Mercury, and Earth, bodies of such different sizes, all have magnetic fields while Venus and Mars don't? And what process could explain the distinct two-phase lunar and paleomagnetic history? However, we do know that core evolution, specifically the mechanism of a purely molten core growing solids, is key to this puzzle, which is why we are developing detailed solidification models to help answer some of these questions. So normally what geodynamicists would do is compare the slopes of the liquid metals cores, adiabat and liquidus, to determine where solids first start to form. I think of this simply as if the adiabat first crosses the liquidus at the center, the core crystallizes bottom up with pure iron solids forming and enriching the liquid with sulfur, and on the other hand, here on the right, if the adiabat first crosses the liquidus at the CMB, you get top-down crystallization, which has been often referred to as iron snow, and depending on the temperature would remelt. And both of these scenarios could drive convection. There's actually more variations with solids forming at multiple places at once or in the middle, but either way, what all of these models assume is that the core is undergoing homogeneous nucleation. And that has been the standard until 2018 when Uge et al. Pointed out the nucleation barrier paradox for the Earth. For solids to start forming continuously, they need to overcome this energy barrier. The nucleation barrier for heterogeneous nucleation requires two things. First, that the liquid's temperature be at least at or below the liquidus, and second, that some substrate be present. For homogeneous nucleation, it requires just one thing, but it's quite more difficult for it to occur, which is that the liquid supercool below the liquidus an incredible amount, a third of the melting temperature for metals, which in the context of the Earth's core would be over 2,000 degrees. The temperature drop is too cold for Earth's thermal history model, so we postulate that homogeneous nucleation is impossible for the Earth's core. And more generally, what Uge's paper demonstrated is that until a substrate is introduced to a system, the liquid can just keep cooling and cooling below the melting temperature. Here I plotted how much of the moon's core, assuming pure iron, would be cooled below melting temperature if the center is supercooled X degrees. Thus, for this compositional end member, we see that around 20 degrees would result in the entire core being supercooled before any solids start to form. Consequently, the only way the solid inner core we have on Earth could have formed is if a metal substrate survived dissolution as it sank through the core and lowered the nucleation barrier at the center. The details and feasibility of this are described in the Gay's paper along with Davies et al. 2019, but what we want to know is how does the nucleation barrier affect planets or asteroids that, because of the possible composition range they're in and their smaller size, could either crystallize bottom up or top down? Which is why we go to the moon. The moon is the optimal body to develop these solidification models we're working on because of the greater level of understanding we have for its current and past states compared to other planets. Specifically, iron-sulfur alloys have been studied extensively at the smaller pressures of the moon's core. We also have structural constraints from geodetic and seismic studies and the paleomagnetic measurements of the Apollo samples that tell us about the moon's really peculiar two-phase magnetic field history defined by an early but short and strong period, and then instead of dying out is followed by a super long-lasting and weak period, for which we still don't quite understand what single or combination of mechanisms resulted in this magnetic behavior. In addition, I'll say that the moon's mantle redox state and other work proposing mass anomalies in the mantle being metal chunks delivered by asteroids makes the idea that metal substrates in some capacity being available at the CMB a fair assumption. And since we don't know exactly what the interior composition or how much supercooling the core experienced, we're creating a suite of models that could be tested by a future network of seismometers, along with the hope that our timing and magnitude assumptions of the paleomagnetic field could be improved by more samples from the Artemis program. All right, so here are the results of our models for crystallization regimes if we ignore the nucleation barrier. This is straightforward. Up to about 8% sulfur, the core crystallized bottom up. Above that, we'll have some ironstone regime. But if you supercool a liquid core with low amounts of sulfur, less than 8%, it will supersaturate all the way to the CMB, which is what I've highlighted here. We see that only 8 degrees supersaturated the entire lunar core, which means that if a substrate is present at the CMB, solids will form at the CMB and not at the bottom of the core, as you would otherwise believe for a core with this given composition. And what we're doing here is describing what could possibly happen for a lunar core with a given composition and a given supercooling. On the very left, we have no supercooling, but it's just reached the liquidus at the very bottom and a substrate has been delivered. So this is as close to canonical growth as possible. Next, we have a core with low sulfur and it's partially supercooled, but not all the way to the CMB. So a substrate still needs to sink. And once it does, all supersaturated dust will solidify extremely quickly, basically instantaneously on lunar timescales. And then on the right, we're introducing two top-down end members to get at just the possible variety in substrate availability at the CMB. Either could describe a low sulfur supersaturated core or a sulfur-rich core. We have the end member here as scarce nucleation sites where dendrites don't interact with each other and then would sink, and then the other end member being where there's so many nucleation sites that it operates as a delaminating layer. And here are some of the results for how big a core would grow during just rapid growth for a low sulfur and only partially supercooled initial conditions. We see that the more sulfur rich, the smaller the core, the solid core that it grows to. And then the more it's been supercooled, the larger it'll grow to. And all of these grow on an order of 10,000 years, which is instant on lunar timescales. If a solid inner core is instantaneously formed, and then you have normal secular cooling growth that follows that, the onset of solids will be delayed significantly. We're also thinking about how for top-down, plentiful nucleation sites, which I was originally skeptical of because of the likeliness of the presence of a solid layer at the CMB on the moon, we found that the mass fraction of these layers are so small, imagine a sponge 90% water, that once it sank, it would compact to a solid core, but while it's at the CMB, where it's not compacted, there's the question of how big could that extremely porous iron layer be without being detected with new seismic data? And there is the piece of how the Lunar Geophysical Network could help us rule out some of the various models we're offering. But for the purpose of this talk, what I would like you to take away is that the nucleation barrier is really important when we think about core formation. No longer can we say for small bodies whether their cores form bottom up or top down based off solely the composition. And furthermore, that a supercooled core will start to crystallize later and very quickly throughout all supersaturated depths. We're exploring currently how that would impact buoyancy flux, maybe affect magnetic field generation with some sort of pulse of energy. And lastly, my work shows that the big takeaway for how the nucleation barrier affects the Earth, where a metal substrate must be delivered to the center, is not true for small bodies with really steep adiabats, because they'll supersaturate so quickly that they can solidify at the CMP. Thank you for your time. And I finished early.
Yes, thank you, Sarah. Thank you for a lovely talk. And if somebody has questions from Sarah, then you can put it on in chat, and Sarah, you can have a look there. So,
with our 2 minutes left, or are we on time to move to the next talk, Wajiha?
Oh, I guess we might have left 1 minute. I stopped this video a bit earlier. We have a time for taking one question if somebody wants to.
If not, we can wait for discussion.
Yes, we can wait
Awesome.
for discussion then.
Great. Thank you so much.
So our next speaker is Marisa Liu, and she will talk about investigating the effect of varying magmatic volatile content on lunar magmatic sand dynamics. Marisa, you can go ahead and share your screen.
There we go. Can you see that okay?
Right, yes.
Yeah, there we go. Okay, is the timer good to go? Thanks, that's great. Okay, yeah, right, thank you. Hi everyone, thanks for coming along to this session. My name is Marisa Lowe and I'm a third year PhD student at the University of Manchester. I'm working with both the planetary science and volcanology research groups here, and my research focuses on understanding volatiles in the lunar mantle using different volcanological techniques. So just to introduce the topic a bit more, the moon hasn't been volcanically active for at least the last 100 million years, possibly even the last 1 billion years. So techniques like sample analysis, remote sensing, and numerical modeling are really key in unpicking what lunar volcanism was like. And as I'm sure you know, volcanism is a common process across the silicate bodies in our solar system, and it's really useful for understanding a wide range of questions. Such as how volatile rich was/is the lunar interior, especially in the context of the evolving giant impact hypothesis, a model of which is depicted on the left-hand side. It's really useful to understand how many volatiles were in the moon to begin with and what the situation is like now. Another question would be, how did magma ascend, and what were the key volatiles that drove ascent? In particular, lots of people are interested in understanding how the most dense high titanium magmas ascended, for example. Another question would be, what were lunar eruptions like? We know what the final eruption products look like, for example, the patches or dark mantling deposits that we can see in Alphonsus crater in the image on the left, but what was the duration and explosivity of the eruptions? And finally, did volcanic outgassing from explosive eruptions ever form a lunar atmosphere? And this is obviously an ongoing area of research with recent papers from Needham and Kring and Head and so on. So the overall aim of my research is to understand the role of volatiles in driving lunar magma ascent and eruption. In particular, the role of volatiles in explosive volcanic eruptions, which produce the pyroclastic deposits on the moon, and like the ones you can see in the image there. So to do this, the first part of my research involved adapting a terrestrial magma ascent model, which has previously been used to answer a wide range of different volcanological questions for volcanoes such as Etna and Stromboli in Italy. But as I said, I'm focusing on the pyroclastic deposits containing glass beads, which were found in the lunar regolith across all Apollo landing sites. So I've been using data on the glass's composition and volatile contents in my model. So from papers like from 2008, Alberto Sal's paper. And the model is capable of simulating magma ascent with magma containing two volatiles at once. So I was testing carbon monoxide and molecular hydrogen, and carbon monoxide and water. So based on redox conditions, molecular hydrogen is the more likely hydrogen species to be dominant in the lunar mantle compared with water. However, when I was adapting the model, I noticed that since water is the dominant hydrogen species in the Earth's mantle, there's a lot more information on, say, the geochemical properties, the solubility of water, all sorts of properties that I need for running the model. So based on this, I wanted to test water as well, not only because there was more information about this, but I could also compare my results with the wealth of information on terrestrial magma ascent. And there's a few key strengths of this model to mention. The first one is that there's a huge number of parameters that can be varied, with over 100 parameters relating to temperature, composition, volatile behavior, viscosity, and so on. And the other main strength of the model is in its holistic approach. So magma ascent is a very complex process. A lot of the factors that govern it are interconnected, such as temperature change, change in rheology, whether crystallization is taking place or degassing. So yeah, main strength of the model is that it takes all of these into account simultaneously. Secondly, I completed a sensitivity analysis using a piece of software called Dakota. I did this to see what effect each of the input parameters had on the outputs. So in real terms, how much of an effect does, say, volatile content have on the way that magma ascends? And the main strength of using Dakota was that rather than me manually varying each of my model inputs and seeing what effect that had on the model outputs, the Dakota toolkit can test thousands of different combinations of the parameters and see what effect that has on the model outputs. So in fact, for each of the 5 end-member compositions of pyroclastic glass bead, I was able to complete 10,000 model simulations. So just to show a few of the results from this. So firstly, from the magma ascent model, I produced these gas exsolution graphs. So we have depth on the y-axis going down to 10 kilometers, and the exsolved gas fraction on the x-axis, which goes from 0 to 1. So the graph on the left is for the water and carbon monoxide model simulations, while the graph on the right is for molecular hydrogen and carbon monoxide. Just to go through the dotted lines represent the minimum initial volatile contents I modeled, which again is based on literature and different measurements taken from the beads. The solid lines represent the maximum amounts I've modeled, and the different colored lines represent either carbon monoxide in green, water or the hydrogen in blue, and the combination of the two in red. So I plotted these to see which gas was the more significant for driving magma ascent, and it seems that for the water and carbon monoxide simulations, even when we're having the maximum amounts of water dissolved in the magma, carbon monoxide seems to always be the main gas driving magma ascent. We see the opposite story with the molecular hydrogen and carbon monoxide simulations. Here, both volatiles are exsolving at great depth, creating a magma that's buoyed by both hydrogen and carbon monoxide. Moving on to the results from the sensitivity analysis, I produced this Sobel index plot. So one of the quantitative ways of showing the results from a sensitivity analysis is to calculate a Sobel index. So the greater the Sobel index, the more of a control the input had on a particular output. So here we have a plot showing, say, exit gas volume fraction and other model outputs against the model inputs, so pressure, temperature, radius, water, and carbon monoxide content. So like the magma ascent model results, we can see that water, shown in red, is not that significant in driving magma ascent or affecting, say, the exit velocity or mass flow rate compared with carbon monoxide, shown in brown, and especially not some of the other parameters, as you can see there. So for comparison, here is a Sobel index plot for the molecular hydrogen and carbon monoxide model simulations. And here the red represents the contribution of molecular hydrogen, and you can see it has a much greater contribution to the ascent and eruption conditions than water did. And this is likely due to the greater solubility of water in magma compared with molecular hydrogen and carbon monoxide. So based on my magma ascent modelling and sensitivity analysis results, For the water and carbon monoxide model simulations, carbon monoxide appears to have a stronger control on magma ascent dynamics than water. And for the hydrogen and carbon monoxide model simulations, we see the opposite. So generally, these results are highlighting the importance of understanding oxygen fugacity, composition, and other conditions within the lunar mantle. That was the main sort of deciding factor when I was adapting the terrestrial model for deciding which volatiles I was going to simulate. But it's not entirely clear how hydrogen would partition, say what proportions it would partition into between molecular hydrogen and water. So in all honesty, we don't know which results I've presented here are the correct answer. I imagine the actual ascent and eruption conditions are somewhere in between the two members I've been running here. So yeah, just as a heads up to finish up, I'm about to resubmit this work to JGR Planets after some revisions. So yeah, please check out the paper if you'd like to find out more, and thank you for listening.
Yes, thank you, Marisa. Thanks a lot. And we have time for one question, if somebody wants to ask.
Marisa, if no one else has a question, and please feel free to put questions in the chat, of course, as you have them. But Marisa, I was wondering if, I know that the sort of standard model for lunar magma ascent, or one of the standard models of lunar magma ascent, it involves very long dikes that reach a level of neutral buoyancy. And I'm wondering if your model sort of sheds light on how close those dikes actually have to get towards the surface before they become sort of, or at least the top mass of them becomes sort of self-buoyant from exsolving gas.
Yeah, I think I have tried to compare my work with those other models, and I think it's quite difficult because a lot of those don't necessarily have a scale attached to them. I think, you know, it's more to do with, say, the amount of magma you have there, the dike thickness. So I think when I was testing this model to begin with, some of the model simulations didn't run, as in the magma wasn't buoyant enough for it to solve. So I think that probably provides like an upper bound as to, you know, how shallow does this magma need to be before it does ascend. So yeah, as I said in this, it solves for 10 kilometers depth and upwards. So maybe in future I could, you know, test how far I could push that.
Thank you. Very interesting.
Yeah, thank you, Marisa. And if anybody has a question for Marisa, please post it in chat. So, so our next speaker is Julie Stopper. Julie, you can go ahead and share your slides. And Julie will talk about Mare deposits in the Australia region of the moon. So I reset the timer.
Okay, thanks. Before I get started, I wanted to acknowledge my co-authors as well: Sam Lawrence, Carolyn Van de Bogert, Harry Hiesinger, and Thomas Jaguar. They've all worked with me on this project for a while, and we've had a great time. This work is supported by the Lunar Reconnaissance Orbiter and camera teams, so I want to thank them as well. So Mare Austral, it's this area on the southeast limb of the moon, right where the star is, between 30 south and 65 south. And if we just peek around the limb a little bit, we have a better view of it. Here is Mare Austral, and you can see that it's roughly circular. It has a low albedo. This area is about 900 kilometers in diameter, and it's been proposed that this is potentially a partially filled, Mare-filled impact basin. However, the more recent gravity and topographic information that we have now doesn't really support a large basin across the entire Austral region. But the work of Newman et al. In 2015 does suggest that there's a smaller degraded basin in the north. It's about 600 kilometers in diameter, but that does leave a broad scattering of smaller Mare deposits to the south that aren't associated with it. And so it also leaves a question as well about, is Mare Austral a good analog for early stages of basin eruptions, the ones that infill them. These would be things that would be obscured in basins like Imbrium or Serenitatis by later massive lava flows. There you go. So in this work, we utilized the newer high-res imagery, the topography, composition, and gravity data to update the crater size frequency distributions, derives new surface ages, and investigate the stratigraphy of the area. And of course, our ultimate goal is to understand the timing of the volcanism here and how it relates to any basin structures. So as I already mentioned, the newer elevation data, and this is the SLDEM 2015 model shown here, they don't really support a large basin across the entire Mare Austral deposit region, but we do see a topographic low in the north where the smaller basin has been proposed. And the other thing to note from the topography is that even closely spaced Mare deposits can have highly variable elevations. So like the three right here span a pretty wide range. And there's also in the area several prominent craters which make really useful stratigraphic markers when we're trying to figure things out. The youngest one is Hamilton Crater, that's the yellow area right here. It's been previously mapped, and this is the USGS Unified Geologic Map shown. This was previously mapped as Eratosthenian. Humboldt up here was dated to about 3.6 billion years in age. And that crater was later modified to have floor fractures as well as some volcanic activity. Right in the center here, we have Jenner Crater. This one's a little bit problematic. It's dated as Imbrium, but the ejecta kind of overlap and mess up some of the Mare in this area. So it's a little bit tricky to get CSFDs out of that area, which is unfortunately in the center of some of what we're interested in. And then to the south, we have Schrodinger Basin deposits. That basin was dated about 3.8 billion years. And you can see some of the rays and scouring marks that continue up into the Mare Austral area, and then they disappear in there. So they are superposed in there by many of the deposits, but some of the craters do actually predate that basin. So in the previous maps, two Imbrian-aged Mare units were identified, and they're shown here in the pink and the reddish colors. And as I said, some of these are superposed by secondary craters from these prominent Jenner, Humboldt, and Hamilton craters in the area. And in the area also, besides the Mare deposits, there are a lot of light plains or smooth plains, and these include likely cryptomaria as well as basin ejecta type deposits. Previously, there has been some study of crater size frequency distributions and derived ages for these deposits, the Mare deposits in particular. This is the work that was done by Hiesinger et al. And that was largely using Lunar Orbiter 4, I believe, and some preliminary Clementine compositional information. And his mapped units are shown here in red. And they derived ages between 3.1 to 3.9 billion years for the Mare deposits. But you can see there's a big central area that's kind of missing any information. So it was hard from this data set to determine whether or not there were any trends across the proposed basin structures in terms of an age progression, because we're missing that information in the middle.
4 minutes.
Okay. And we were fortunately able to make use of the newer WAC and Kikuya terrain camera mosaics to look at morphologies as well as to derive additional CSFDs. And this is nice because it allows us to use the consistent illumination and scale of those products. So we have some cutoff diameters for the minimum diameters that we included in our analysis. So from the WAC mosaics, we cut it off at a 500-meter diameter, and for the Kaguya dataset, 300 meters. But it's worth mentioning that some of these reached equilibrium diameter at diameters greater than those, and so we would use a different limit in those cases. So all of our areas were shown in pink on that image, but we're also looking for other clues besides just the CSFDs. We're looking for things like using the newer available compositional information to look for different flow units. So this is the familiar now Clementine UV-Vis iron map, and this is Lyo crater in Austral. And you can see in this map there's two different units within this crater, and one is younger and more iron rich and more titanium rich than the older deposits. Some of the other things that we are able to do now are look for flow features and morphologies that were not previously resolved in the older data sets. So we have the goal of looking for potential interconnections between deposits, looking for possible pathways for flows, possible vents, and this is with the goal to help us constrain the number and volumes of eruptions that actually occurred.
2 minutes.
Okay. And this is an example of Barnard D here. And in this area, we have in the topography some potential flow paths as well as some morphologic indicators that there was probably flow between Barnard D and the surrounding areas. And that's consistent with the ages we derived of being just about the same for those deposits. So to summarize what we've been doing so far, we've been refining the number of flows and vents as well as the timing so we can understand this area better and its relationship to any basin structures. So far, our results show that volcanism in this area ended in the North Austral Basin area. So that's this area up here by Abel and Barnard D, and as well as in Humboldt crater. And that was about 3.4 billion years ago. There's lots of other volcanic deposits in the area, eruptions that mostly occurred around 3.6 and earlier. But this results in what's pretty much a really narrow range of volcanism, about 500 million years. There's of course some earlier cryptomaria as well. But compare that to like Imbrium or SPA basins, where volcanism continued until about 2 billion years ago. So in that sense, Austral might indeed actually be a really good analog for early basin eruptions because we're not seeing those later deposits or later eruptions. So that's what I have for today. Thanks. I guess I can take questions. It looks like I might have a couple of seconds left.
Yes, thanks, Julie. So there is one question for you in chat from Catherine. Yes, and she asked, how would you differentiate volcanic flow features from impact melt flow features?
Oh, okay. That's an interesting question. For the most part, like it would be in terms of context. So melt flows generally occur with really close to the crater rim, but I assume you're asking about inside the crater, like a deposit in the floor. And for that, it's a little bit trickier. For most of these craters, we see that they have an iron enrichment that is stronger than what the impactor target would have been. So that's pretty much our assumption there.
Thanks, Julie. And if somebody else has more questions with Julie, please write them in chat and we can discuss them in discussion session. And with this, I can hand it over to Jacob.
All right, well, I'll be introducing the second half of our session. And I'll start with Williams, Edward Williams will be talking about effects of lunar lava tube shape and dimension on internal failure and external observability. So Edward, if you could try to share your screen.
Oh, okay, thanks. Sorry, let me just get my PowerPoint in the right.
And I'll also note that co-author is Montesi.
Sorry, I'm just trying to share my screen properly. Okay,
all right,
can
we can see this. Yes, and Wajiha, can you reset your clock? All right, you're good to go, Edward.
Okay, thanks. Sorry, I'm just trying. Okay, so hi, I'm Edward Williams, and I've been studying the internal usability and surface observability of lunar lava tubes. So just for some background and introduction, lava tubes are long subsurface void spaces left by lava flows. They exist on Earth, and we also have evidence indicating that they exist on the Moon. A lunar lava tube would potentially be an ideal environment for exploration or habitation on the Moon in the future. So the goals of this research were to model lunar lava tubes to determine their internal stability and how they can be located and studied from observable surface features. So some of the evidence that we have indicating that lunar lava tubes exist include observations of sinuous rills, which are winding troughs on the lunar maria. These are believed to be related to lava tubes since they have related formation mechanisms, and they can be connected to lava tubes or contain tube segments. We've also observed holes on the lunar surface, which we think are skylights into lunar lava tubes. And also we have gravity data from GRAIL and ground penetrating radar data from the lunar radar sounder, also indicating that lunar lava tubes exist. So I've been using finite element COMSOL multiphysics 2D models to simulate lava tubes. I used an idealized lava tube shape that you can see here on the right, which is a half ellipse with a width-height ratio of 3:1 and a rounded corner. I varied roof thicknesses and tube widths, and I determined regions of different types of failure on the internal surfaces of the tubes and on the surfaces above the tubes. This was for my main models. I also did some model variants using different tube shapes. I changed two aspects of tube shape, which were the width-to-height ratio of the top half of the tube and the floor curvature. The width-to-height ratio of the top half I changed from 3:1, which was the original shape, to 6:1, which was a flatter version, and 2:1, which was a semicircle. And the floor curvature I ranged from a flat floor to a semicircular floor. And I found the maximum tensile floor stresses for these tubes of different shapes and compared them. I used an elastic rheology for my models with a shear modulus and Poisson ratio that you can see here. I used plane strain assumptions, and my models are simply loaded by gravity with the density of the material and gravitational accelerations that you can also see here. For failure criteria, for tensile failure, I just used a cutoff at the tensile strength of the rock. And for compressive failure, I used the Hook-Brown failure criterion. These needed strength parameters, including these needed parameters, including the GSI, or geological strength index, and other strength parameters for the rock. You can see the values that I found were calculated for these in this table here. So this is an example of one of my model results. The sort of dark blue to white shading is showing how close the rock is to compressive failure. And it's white where the rock is in compressive failure, although this doesn't actually occur in this model. And shaded red is showing where the rock is in tension, and the red circles are showing tensile failure on the roof and floor of the tube. So I found, I studied several different types of failure inside these tubes, the most extensive of which was tensile failure on the tube floor. I found that this was present in all but one tube, and wherever it was present, it covered most of the floor, over 65%, and in some cases covered almost 95% of the floor. I also studied tensile failure on the tube roof and compressive failure on the tube wall, because I found these three types of failure were found to be present inside the tubes. And the combination of these effects meant that most of the floor was interrupted by cracking or debris and was difficult to use, and it was expected to be difficult to use. I characterize usable floor as any region of floor that isn't interrupted by cracking and isn't directly underneath any region of roof that's failing but could be dropping debris onto it. I found that the maximum usable floor extent for these tubes was 500 meters. This was generally greater in shallower tubes, but did not depend predictably on tube width. And also, additional factors not captured in these models could cause further failure to occur. These are the results of my models with different tube shapes. I found that increasing the curvature depth of the tube floor decreased the floor tensile stress and made failure less likely, and increasing the width-to-height ratio of the top half of the tube increased floor tensile stress. You can see this plot, the y-axis is showing the maximum tensile floor stress, The x-axis is the floor depth, and the different colored lines are showing the different top half shapes that I used. So that was what I found for the internal failure inside the tubes. I also studied the surface features created by the tubes on the surface above them. I found that each tube is expected to cause two regions of tensile stress buildup to either side of the tube. These are expected to be highlighted by tensile cracking. I calculated the distance for each tube from the center of the tube to the location of tensile surface stress. I found this distance depends predictably and linearly on tube width and tube roof thickness. And this relationship could be used if we can find this surface feature to determine the width of the tube from the surface. I also studied a similar distance, which is the distance from the center of the tube to the peak of the elastic bulge that it causes on the surface. And I found the ratio of these two distances to be constant. I think this ratio could be used if we can find these two surface features, but if we can't find the tube itself, to determine the location of the tube. As well as my modeling, I also did some observations of the lunar surface using the LROC QuickMap tool. I looked at LROC imagery and other available data sets. I studied sinuous rills and surrounding areas where I thought lava tubes might be present. The results were that in most locations I didn't see thanks. In most locations I didn't see the expected clear linear cracking patterns that I was looking for. It's possible they were present but undetectable due to regolith buildup, degradation over time, or just that they were too small to detect this imagery. However, there was one location where I did see the kind of linear cracking patterns that I expected, which was the southern end of Rima Myran. I found two lines of cracking that continue the path of the rill and connect two large aligned depressions, and I think this suggests that the rill continues into a tube. So this is now my discussion of my results. I found that I think my findings about usable floor regions inside the tube could have multiple different implications for future lunar missions. They could constrain the sizes of planned lunar bases, and also since I found usable floor region to be only near the edge of the tube, this would mean that if we entered the tube through a skylight and arrived at the center of the tube, we would need a way to traverse over a damaged floor. Also, since the usable floor regions near the edges, direct overhead access to a skylight for things like solar power will be impossible, so we need to find some sort of way to work around this. Also, a method of clearing debris from the floor would be useful, and inflatable structures, if they're used, should be reinforced to account for the large amounts of debris and cracking expected that may have sharp edges. Also, since I found that usable floor extends for larger and shallower tubes, if we can determine the roof thickness of a tube from the surface, such as from angled imagery, we could use this to prioritize choosing shallower tubes to explore. These are the surface feature relationships that I described earlier. I think these could be used if we can determine the surface features to study the tubes, as I described earlier. And my results about tube shape, I think also could be applied to future lunar missions. I found that the most usable floor is present in tubes with curving floors and low width height ratios, so these may be preferable to choose. However, there are also drawbacks to choosing a tube with a curving floor, since a flat floor may be more advantageous for walking on or constructing things on. So I think both of these factors should be taken into consideration when choosing a tube. And finally, I found a candidate lava tube extension of Rima Myran at its southern end. I used the surface feature relationships I described to calculate an approximate width for this tube of 200 meters. I think relatively little failure is expected in such a small tube. And I think other such candidate tubes could be found in the same way in other rills or using other data sets, or possibly in the future using higher resolution observations from the lunar surface itself. And here I have just a summary slide of my conclusions. Thank you for listening. Are there any questions?
Thank you, Edward. It looks like there are a couple of questions popping up in the chat. I'll read out the first one, which is Ichi asks, why do you think the source of Rima Myran a lava tube rather than the surface expression of a dike instead?
Oh, right. I guess I was thinking that for one thing, it struck me that it's sort of the fact that it connects these two aligned large depressions, and the large depressions sort of follow the same line as the cracking does. I was sort of, I guess it was making me think that if this were the depressions would also fit with if this was indicative of a tube, because it could be that the tube is partially collapsed, which could also explain that sort of oddly shaped depressions.
All right.
Well,
thank you. Oh, go on.
I was just going to say that also it was very similar to the sort of patterns that I was expecting to find in my research, so that seemed indicative of a tube to me.
Well, very interesting. I think that you can answer that question and another question from Josh in the chat while we move on. Okay. Very interesting. Now, I guess it's time to move on to Samuel Hullum, who is going to be talking about modeling carbonaceous chondrite survival, a potential resource cache on the lunar surface. And co-authors are Crawford, Collins, Joy, Davison, and Davidson.
Brilliant, thank you. Right, where is this? Is that sharing properly?
Yes, just fine.
Excellent, thank you very much. So I'm going to be discussing today a little bit on part of my PhD project that I've been working on, looking at the survival of carbonaceous chondrites after they impact into the lunar surface. So firstly, why do we care if they survive? So the main reason is looking at what is lacking on the lunar surface for the next phase and beyond of lunar crewed missions. So looking at lunar geology here, we've got a couple of maps of the lunar surface showing that they're rich in things like iron, titanium, silica, oxygen, things that we know in minerals like ilmenite, as well as things like aluminium and calcium on the far side of the moon. We've also heard a lot of things about how the polar regions are very rich in volatile material, including water that we're obviously very interested in the terms of crewed missions. And these are usually found in concentrations around PSRs or inside PSRs. And so we're also thinking now about what could be done beyond this. So one thing that we're looking at is carbon on the moon. Carbon, a very useful resource for crewed missions. Also industrial Canon, some work by Canon this year, showing the total carbon abundance versus the concentration for the inner solar system resources. So this is kind of concentrating on the moon and Mars, and looking at where carbon can be found on the lunar surface. And to be honest, it's a small amount, and it's spread across the lunar surface. So these resources of carbon aren't very great from a resource point of view. They're not very concentrated, and so if there was a crewed mission, it'd be very hard to use all of it very well because it's so widespread. So I'd like to add one to this list, possibly carbonaceous chondrites, because of the significant lack of high concentration and accessible caches of both carbon, and also we're thinking about nitrogen native to the lunar surface. And carbonaceous chondrites have a few properties that we're really interested in, but the main one that I want to talk about is their high carbon nitrogen content. This is both organic and inorganic, and it can be up to 6, even more weight percent in some samples that we see. 6 weight percent and 0.5 weight percent for nitrogen. So this highly rich organic material in these carbonaceous chondrites could be a really good resource if they land in a way that's favorable to their survival and concentrates them in a small area. So an example of a quite rich organic sample is Murchison, a CM2, and it has organic matter in it with almost 2 weight percent in some cases, and also some even hardier carbon materials like diamond, graphite, and silicon carbide. These are in much lower abundances, but they're much better at surviving high pressures and temperatures. So they're very interesting in terms of a resource point of view after an impact. Also, there's some amino acids that I'm looking at, including glutamine, which has a pretty good vaporization temperature, as seen here, 850 Kelvin. So we're looking if the things can survive these temperatures and pressures after impacting the moon. So the resource potential, we're looking at 2 things. Are the pressure and temperature regimes suitable post-impact? And where does the projectile material end up? And so I've been using hydrocode modeling, specifically ISAIL3D, to look at this and creating these scenarios with a carbonaceous chondrite-like parent asteroid impacting a basalt lunar-like surface at these varying impact velocities and varying impact angles. And this is a 3D code that allows us to look at materials traveling through a mesh that has cells that are filled by this material. And then also in the projectile, we've put tracers that can track the pressures and temperatures, as well as other parameters across the scenarios that we run. So this is what it looks like from a cross section. This is an impact from right to left at a 45-degree angle. You can see the projectile material in black impacting into the yellow target material there. So just as an example of a cross section of this 3D model. So some general thresholds that I was looking at include the melt temperature of the projectile, looking at what melts and what doesn't. It's a really good way to see how things might stay in place after they've impacted. Something that's melted or vaporized is more likely to escape and move around after impact. So we're looking at what's not melted, and then some other temperatures for carbonates and amino acids and other things that are likely to survive. So some results for that. Looking at the different impact scenarios we've got, this is a table showing the percentage of the projectile material that survives and remains solid according to the peak temperatures reached within the projectile. So it's 100% for the lowest impact angle and the velocity, and it goes down to 0% for anything over 30 degrees and over 10 kilometers per second. Now, if we look at this from a resource perspective, as I talked about before, we want to look at the concentration of the mass surviving. And so this is what we'll look at here in these top-down views of the remnant projectiles that remain. So this black material here represents all material that remains between 1000 and 2000 Kelvin. So all of this hasn't melted. And you can see that a lot of this, the majority of the mass, remains within this red dashed outline. So this is top down looking at the crater. And so this is less than 2.5 kilometers. Thanks. This is less than 2.5 kilometers in diameter. It's highly concentrated. All of the material is less than 10 kilometers from the impact zone. But no material survives less than 1000 Kelvin in their peak temperature. So no nitrogen is likely to survive here. It's all pretty much vaporized and been lost into the wider area. However, if we look at something like the highly oblique impact at 15 degrees from the horizontal and 5 kilometers per second, the lowest the impact velocity that we tested, we have 30% of the projectile that reaches temperatures of only 750 Kelvin at a maximum. And this is widespread, but it's actually concentrated downrange in a process called projectile decapitation, where a large mass of the projectile splits off from the impacting zone and travels further down range and impacts at a slower velocity and hopefully concentrates, as we see here, slightly downrange. Talking about the accessibility, just kind of building on this, most of the material is in one place in these highly oblique, more vertical impacts, so there's 60 degrees. But the simple lunar crater may have steep walls and a lack of a flat floor that may not help in the accessibility factor of this material. But there probably is a lot of carbon that survives in one place here. If we're wanting to look at material that survives at lower temperatures, so with more carbon species and with the potential for amino acids to survive with their nitrogen, most of that material is going to be spread over a wide area, but some of it in this decapitated portion of the projectile could be concentrated downrange and be a potential resource if it's concentrated like this. So these are two kind of the extreme end members that I looked at, and there is a whole range of different survivability within this, which I obviously don't have time to show here, but there is survivability in a lot of other of the impacts as well. So just to finish off with some conclusions, I'll leave them up there, but the main thing is that we do see survivability of some carbon species and a good amount of concentration in smaller-ish areas that allow for their potential use as a resource in future. Thank you.
Thank you, Samuel. I think we have time for one question, so I can read out Schweili's question. Is it possible the vaporized materials will condense back to the lunar surface? And if so, any estimate about the portion of materials coming back to the moon?
That's a really good question, and it's something we've considered. These are definitely conservative estimates that I've got up here of the amount of surviving high temperature material. We just wanted to look at what remains solid, and it's easiest to say definitely stays in one place. But yes, it is definitely possible that some material could recondense. As for a proportion, I couldn't say anything on it yet, but there is more work to be done on this to look at that, yes.
All right, well, thank you. I think we can move on, and we're running just a couple minutes late, so we can catch up now. The next talk will be given by my illustrious co-chair, Wajiha Iqbal, with Hiesinger, Vanderbogert, and Head as co-authors on a source of young ages at Apollo 15 landing site. I can actually time for you, Wajiha, so please take it away. And I think you're muted if you're.
Sorry, too many buttons. Yes. So now you can hear me?
Yes, I can hear you fine.
Okay, so probably you can see me now too. So in this presentation, I would like to propose a source of the young ages, which were noticed in the samples collected from Apollo 15 landing site. And this study is a small part of a bigger project in which we are testing and we are possibly improving lunar crating chronology function. So as I noticed today, we have people from various geology field here. So I would like to describe a little bit what lunar chronology function is here. So on y-axis, you see a logarithm scale, which is represented by the value n1. And this value you gain by measuring crater size frequency distribution. So in general, I can say this number is representing crater density of certain geological unit for certain range of diameter. In this case, here is a 1 kilometer. And on x-axis, you see time, and you see time in billion year, and this time is normally considered from or taken from isotopic ages of the samples. So how do you calibrate this calculated lunar chronology function? For this purpose, we prepare detailed geological maps of all landing sites. And then we identify a homogeneous area, geologically homogeneous areas on this geological map and measure CSFTs. And from there, we get N1 values that we represented on y-axis. And then we also investigate composition and isotopic composition of these samples and isotopic ages that were determined through these samples. And that's what we represented on x-axis. And by correlating these two values, we could get a calibration point that can confirm as validity of this chronology function. So as I say, for preparing geological maps, we use wide range of data. We use a lot of data that is like image data, for example, LRO, WAC, and NAC images. We use different DTMs, and we use various spectral data. And we use this data on different resolution. And with this information, we can prepare very detailed geological map, and we prepare the geological map for all landing sites. And here I'm presenting a geological map for Apollo 15 landing site. So this is overview around the Apollo 15 landing site, and this green triangle in middle represent position of the lunar module in the east of Rima Headley. We use spectral data to map various Mare units here. And here, what is different from previous maps of this area is that we mapped Aristobulus and Autolycus craters at the red Justinian, on contrary to what previous authors map or people map these craters as Copernicus. And this is decided on base of CSST, relative positioning. And also we noticed that this ejecta material from Aristobulus is different due to the compositional differences. We also prepare a geological map that is a more detailed geological map around the lunar module. Here again, green triangle is representing position of lunar module. These dotted lines are representing traverses that were taken by astronauts to collect samples. And what we notice here is most of the traverse and lunar module is present on a ray material that is coming from northwest direction. However, there are also kind of young craters around this traverse, like Bridge crater or St. George crater, that could also have material present on these traverses. So so in most of the samples that was collected, most of the regolith and impact breccia samples that were collected on this traverse contain class of creep-rich basalts. And there are also some samples that were collected near Spur crater, which are actually samples of creep-rich basalts. But some of these samples show age of 2 billion year, which was interpreted to be that they were heated in a common event around this time. And this age of 2.1 billion year is mostly correlated by Bogart and Ryder, for example, with Autolycus crater. Yeah.
4 minutes.
So but here I'm showing you a thorium map in comparative to our drive geological map. And what we know here is that area around the landing site is deficient in thorium. And being deficient in thorium means that they are lacking creep-rich material, which means that the Mare basalts that are around this lunar module are not creep-rich. So there are 2 points. So there are 2 points in blue which are showing higher thorium anomalies. That is one near in the south of Archimedes crater. And this area is normally in older maps are mapped as opinion bench formation here. However, in our map, we noticed that it's a mixture of many different formations. It's a mixture of ejecta material, light plains, and various mare. However, the pure thorium anomaly we noticed around Aristelis crater, and this the extent of this this anomaly is very consistent with our mapping units as well. So it means that if there is a creep-rich material coming on this near landing site, it is possible coming from Aristelis crater. So considering that in mind, we try to get some N1 values for Aristelis crater, thinking that it might be also around 2.1 billion years. But getting ages on younger crater is very tricky. You have to deal with a lot of secondary craters. There are too many slopes. So it is very difficult to find these N1 values on young crater. We use several data. We use back data. We use Kaguya data. However, on NAC data, we could determine 2 reasonable areas on crater terraces, and we got consistent N1 values for this area, which also indicate it could be of 2.1 billion year old. However, because these areas are too small, we are concerned about also errors on these areas. And anyway, if we take these values, N1 values, what we gained on these areas and correlate them with the sample ages of 2.1 billion years, we are able to get a calibration point for lunar chronology function. And this gain calibration point is again very consistent with measured lunar crater chronology function that was measured, that was derived by Neukom in 1983. And that's it for my talk. Thank you.
All right, thank you, Waishiha. Are there any questions in the chat? I'm not seeing any right now. There is one here, again from Ichi, who's asking, I may have missed something. Are the materials from the 2.1 billion-year-old crater sampled? If not, how does it help calibrate lunar chronology function? Oh, and I think you're muted.
Okay.
Yeah,
Sorry. Yeah. So 2.1 billion year age has been found in samples. So it was age found in impact fracture material that was in creep basalt samples. And this was it was considered that it was reheated. This basaltic material was reheated at 2.1 billion year. And the idea was where this age can come from because it is transported there. And we were looking for a source where it is transported from.
All right. Well, I think we can move on to our final talk. If you'd like to reset your clock background, our final talk will be given by Talkington with co-authors Hirabayashi, Montalvo, and King, and the talk will be reduction of crater populations greater than 600 to 800 meters in diameter on the walls of the lunar complex craters from mass movement events.
Hi. Okay, so I know that's quite a title.
It's a great title.
Thank you. Thank you. Okay, so as previously said, my name is Lauren Talkington. I'm a current master's student at Auburn University, and this is a bit of my research that I've done over the last year. So as an introduction, we know that craters on the moon are constantly exposed to numerous impact events post-emplacement. And because of this, topographic diffusion is slowly degrading the simple craters by emplacements of smaller ones on top and around them. And we can see the different rates for this in comparing Scott and Amundsen. So these are both complex craters that are found within the lunar southern pole, and they're both around 100 kilometers in diameter. And our initial observations that we can see in Amundsen are the evidence for steep walls, clear rim features, terraces, and a central peak. However, these features are lacking in Scott, as we don't really see the evidence of a central peak or the clear rim features. In addition, the walls are a lot less distinguishable from the floor region. And the observed terraces in Amundsen gave us a pretty important understanding in understanding what happened here post its original emplacement. And we believe these to be remnants of landslides or mass movement events. And this observation was fundamental in our research because we explored how topographic diffusion affects complex crater degradation. And we did this by looking at the crater populations found on complex crater walls. So in our study, we looked at the morphologies of 16 complex craters found on the lunar southern pole to better understand their wall degradation and how it's influenced post-emplacement by meteorite bombardments. So we use LOLA DEM data from the PDS Geosciences node at Washington University of St. Louis. And within the DEM, we collected our data by crater counting along the walls of the complex craters using ArcMap and the Crater Tools add-in. So the first thing we did was add the DEM into ArcMap and used a slope and hillshade overlay so that we could actually see the surface in greater detail. And from there, we started an editing session and created two shapefiles, the first of which defined the wall area and the second, the crater counting layer. And within the crater counting layer, we used the 3-point crater counting method, which just uses 3 points that we click around each crater and extrapolates the rim by connecting them. And so once we had our crater counts, we wanted to find the slope conditions for these counts. And the reason behind this was so that if we could see what diameters were found at certain slope regions, we may be able to see some instances of the relative wall strength and find out more about that. So we use the buffer analysis tool as well as the add surface information tool within ArcMap. And what that does is it takes the information from our slope layer that we previously had and can calculate an average slope within that buffer around the outside of the crater rims. And we completed that process for 16 complex craters, equaling 7,905 counts in total over an average area of 2,205.06 square kilometers. And to make sure that we were kind of keeping our counts pretty equal here over all of our bases, we defined a crater as a circular feature with a central depression. So features that did not fit this, we excluded. So this is an example of what our results look like when we finish crater counting. In contrast to the floor, the walls are sloping. So we had to really stay put and say, okay, this is what we're gonna determine as a crater. This is what we're gonna omit. And in doing that, you can see in the legend here, the wall area defined in blue, as well as the craters themselves. We counted craters from 99 meters to 9 kilometers in diameter. And in addition, the slope variations on the walls are also presented there within the legend. Okay, so to get our results, we compiled the counts and used Python to create some plots just to visually analyze everything. So by just looking at the histogram, it's pretty obvious what the largest crater population belonged to. This was the less or equal to 700 meter diameter craters. And this bin alone had 7,251 craters. In addition, we can see that these craters range in slope values from very shallow to relatively steep or pretty steep. Whereas in contrast to those greater than 700 meters, there's a much less number of them. There's a lot less of them, as well as they're much tighter constrained slope-wise. And also looking at our CSFD, this is all of the 16 CSFDs that we compiled. We noticed a transition in populations greater than 800 meters, which this is indicated by the 2 black dashed lines ranging from 600 to 800 meters. Okay, so we also wanted to calculate the shear strength in addition to investigating our landslides here. So shear strength is determined by looking parallel or along the wall surface. And we determined that if we can derive the lower bound of necessary conditions to produce landslides, this is what we would need to take into account. So first, there would need to be a landslide thickness of 180 to 240 meters in thickness, which is also the transient crater diameters for those of that transition we previously mentioned. And next, we would calculate the necessary or shear strength that would prevent the landslide from it even happening. So to do this, we used rho times gravity times height, sine of the slope angle. And we interpreted that since the slope would already be determined before the craters were in place, finding the derived strength would serve us as a lower bound for the production of landslides. And we deduced that the occurrence of landslides themselves, thank you. The occurrence of landslides themselves may serve as the upper bound. Otherwise, the strength would be able to withstand the impacts and the landslide itself would not happen. So using our derived slope strength of 0.5 to 0.7 megapascals, we can interpret that the walls structurally weaken due to the emplacements of the hosting craters and post-dated smaller craters. So the depletion of craters with diameters greater than 600 to 800 meters implies that landslides would be large enough to erase those morphologies. So to determine the characteristics of strength within the gravity and strength regimes, we first need to define a few things. The first is the F ratio, also known as the impactor to crater size ratio. And to make this plot, we assume that the impactor speed was 15 kilometers per second and that the target density and the impactor density were identical. So the F ratio ranges from 30 to 45 in the gravity regime due to the weaker strength associated with the size ratio. And when F is equal to 10, the strength reaches about 125 to 305 megapascals. Our red line here describes the strength to gravity transition at 1 megapascals. So that is very important pointing out, because if we can determine that the craters found on the walls belong within the gravity regime, this is conclusive with our results that show that there's a larger population of the smaller impacts rather than the larger ones, because these are not capable of producing landslides. So in summary, we deduced that the largest population would belong to the 700 and below, and that this is because they're not capable of producing landslides. We also noticed a transition found at craters with diameter 600 to 800 meters in diameter, and we attribute this transition due to landslide erasure of wall morphologies. We further investigated this transition by using crater counting and impact crater scaling relationships, and can derive the necessary or shear strength, giving us our lower bound for the wall strength at 0.5, 0.7 megapascals. And because of this, impactors capable of forming 600-meter craters did not have enough energy to induce landslides. And the transition we noted is due to the larger impactors having enough energy to induce these landslides and causing partial or total erasure of those cavities. And our calculated shear strength may be 0.5 to 0.7 megapascals, implying variations in the strength in fragmented and unfragmented surfaces. And finally, we determined that if this is the case in furthering this research, we must account for the strength variation due to the presence or lacking of water ice among specific complex craters and to assess the impactor's physical properties carefully. So some final thanks I would like to give are in support of this project are from the Geosciences Department at Auburn University, and also our research would not have been possible without the use of DEMs from the PDS Geosciences node at Washington University of St. Louis. And thank you all for listening. I really appreciate it.
Thank you. Any questions, please put them in the chat. Catherine Niche has asked, has said, nice talk. I think you mentioned that the crater counts on the walls are lower than the surrounding region. Is this because the landslides are covering up smaller craters downhill from the impact?
That is a good question. So I know I don't want to make you like fast type really quick. When you mean the surrounding region, do you mean compared to the floors or the exterior of the wall? Because compared to the floors, there's definitely a much smaller number, both either, okay. So compared to the floors, I know there's definitely a lot less. So let's make sure I get this. Oh, thanks, Pedro. Let's see. Sorry, I'm getting messages here. Okay, so within the smaller impactors themselves just being more prevalent, we just noted this just because we see more impactors that are within that smaller range or more craters within the smaller range on the walls rather than the larger ones. And we just deduced that this would be from these events not having, or these impactors not having enough energy themselves. Whereas if a larger impactor were to come in and hit the surface, it would have a likelihood of covering up its emplacement. And I assume as well, other smaller emplacements nearby and around it. But yeah, we're still working as hard as we can on this. But yeah, thank you for your question. I hope I answered it correctly for you.
Right, thank you. Well, I think that we can spend some more time answering questions. So we have about a half of an hour until our networking event. So before we transition into our discussion time, I'd like to point out that we have a networking event. I believe that it is in conference room 1. It's in Gathertown Conference Room 1, and it is at the top of the hour in whichever time zone you're in, unless you're in Nova Scotia. So with that, we have about half of an hour for people to write questions in the chat and have our speakers, who we'd like to thank, answer them. Oh, Newfoundland. Okay, thank you. And if and please feel free to raise your hand if you'd like to speak out loud. I think that we can open that up as well. We have a question in the chat from Ichi again to Josh, which is how much difference do different methods have when dating the same rock or crystal? And I'm not sure, is that, Ichi, maybe you would go ahead and unmute. I'm not sure if you're talking about crater counting or if you're talking about radiogenic isotope dating.
Could you hear me?
Yeah.
Oh yeah, I'm talking about isotopic measurements because Vagila and some presenters talk about this, and actually I found that ARL Archean dating is looks much younger than like the PB dating, and I want to know how many difference does different isotopic methods have, and I know Josh is an expert of this field.
Thanks, Yuji. I mean, it gets back to, I guess, the question I was asking Wajia. It's not really a simple answer, but different methods rely on kind of quite, I guess what we refer to as like different resetting temperatures. So things like argon we know are much more easily reset in the mineral systems that we look at compared to the uranium lead system, for example. And so it could be different events that are causing those ages. So so for example, when Wajir is talking about 2.1 billion year old ages, they're not actually, or they are almost certainly not going to be the formation ages of those basaltic, those creep-rich materials. There will be some later event that modified them. But yeah, so it's kind of interesting though. I guess my question to Wajir was all about the fact that, I guess, if you're comparing these different things, you have to always be aware that your decay constants that you use to calculate the ages will constantly kind of get revised, and it's just always good when you're comparing different isotope systems to try and keep those in line as much as possible, so you can have a good idea of what your absolute ages are.
Thank you. Feel free again to raise your hands if you'd like to speak out loud or write a question in the chat. I had a question actually for Lauren, which was, you mentioned ice at the very end of your talk, or the presence of ice. I was wondering both if you've thought about how much ice might change that, I guess that size threshold that you've described or observed, and also does the size of crater actually tell you something about maybe hazards analysis when we're going to be sending rovers or even humans into some of these PSRs in the future?
So within our research at this point, we have not included anything with regards to strength variations or anything containing water ice. So I just bring that up as like in the future, like in the event, because it would be very integral in looking into that, because it would obviously change the conditions of which you're looking at it. In addition to how much, I guess, what's the word? So in addition to changing the strength conditions, it would also change what the crater populations you would find there are, because it would also alter those as well. So in the future, hopefully.
Wajiha, do you see any questions, or do you have a question for anybody in the audience?
Oh, yes. So I do have a question from Edward, and I'm not sure if I missed it or was it there. I didn't see any sector of time in your model. So I was thinking that if you're talking about collapsing, then which model will fit which time range? How long do you expect them to fail?
You mean like how long would I expect them to like stay stable for before failing?
Right.
Okay. I guess I'm sort of, yeah, I didn't really have a time aspect in my models, like it wasn't evolving over time. So I guess I'm just working on the assumption that any lava tube on the moon has been there for so long that any collapse that would likely to occur has already occurred. So I guess I'm not really trying to figure out, and it isn't really evolving with time. I'm not trying to figure out when things would collapse, just like if they would collapse or not, I guess.
Go on.
Yeah, sure. I was thinking in a way that if you talk about these lava tubes, you're more concerned about that could be habitable in future, and that's where the stability ideas comes from, I guess, or?
Yeah, I was thinking the stability idea for I was thinking the impact of stability on habitation would be more like, not like if it was going to collapse while people are inside it, but just like if it's collapsed at some point in the past, if it would have left like chunks of debris on the floor or cracks that would make the floor difficult to use or anything like that. So I'm sort of assuming that any collapse has already happened, and I'm just trying to figure out how much damage that collapse has caused, I guess.
Okay.
Did that answer your question?
Yes, thank you.
Yeah, thanks. Thanks for the question.
And then I actually had a follow-up, I guess, which is I noticed in your talk, or you made a point in your talk that you have tensile fractures or tensile failure at the bottoms of some of these large tubes. And I'm wondering, is there a threshold of tube size that you see where, you know, at, you know, a certain meter diameter smaller tube, we can go in and expect maybe a pristine floor, whether or not it's piled on with roof collapse, but a pristine floor?
Yeah, I think so. I mean, for the ranges of size that I used, all but one of them had tensile floor failure, but I think it was the very smallest and narrowest of them didn't have any floor failure. It was, I think, 500 meters wide and a roof thickness of 50 meters. And that was the only one that didn't have any failure on the floor. So I haven't yet, but I might do some more test models of just like a very small sizes and very small roof thickness like that to see if models that are that small also don't have any floor failure.
Thank you.
If anybody has a question, they can also raise hand and ask directly.
So as we're waiting for fervent questions to roll in, I'll just one more time tell everyone to meet in the GatherTown Conference Room 1. We're number 1. To just mingle with other geologists for our sort of session networking event. And that will happen at the top of the hour in whichever time zone you're in, again, except for Newfoundland. All right, we have Toshi Hirabayashi has asked Catherine regarding landslide, or has given an answer to Catherine, which I think you could find in the chat.
If you would like to discuss it, you can turn on your microphone. And
yeah, yeah. So this is Toshi. So I was working with Lauren. So regarding question from Catherine, I added some comment on that. Basically, we observed smaller craters, or technically like smaller than 700 to 800 meter diameters than larger craters. So our interpretation was that so smaller craters can exist on the slope, but larger craters cannot. So our interpretation was that because of this, larger craters can bring higher kinetic energy to fragment the surface, the slope, but the smaller ones cannot. So because of this, we considered enhanced enhanced landslides will be the key contributors to degrading surface slope. This is what we are thinking.
Thank you for that explanation. Samuel, I think you have your hand raised.
Yeah, I've got a quick question for Marissa about the modeling, if she's still around. Yeah. Do these models pertain to a particular size range of lava, of ascension? Is there a particular size that these are particularly applicable to?
Yeah, so it's modeling magma rising within. You can set the diameter of the dike. So it is assuming like a more circular or oval shaped dike rather than, as we know, they're probably more sheet-like in reality. So yeah, I mostly based the sizes of it. Well, there are some measurements for like lunar dikes, which are based on like satellite measurements, you know, sort of the gravitational anomalies that you can get. But the detection limits on those are for like kilometer scale dikes rather than like meter scale ones, which were the ones that I was picturing. So I sort of went for a bit of an in-between between these geophysical measurements and like dike surveys on Earth. So yeah, that is something that you can play around with in the model.
Does it make a massive difference on the dynamics if you change it significantly?
Yeah, so based on that sensitivity analysis, the main thing I was seeing is that it was affecting like the mass flow rate. And yeah, it has a really strong control on that. So yeah, it's a difficult one to constrain that does have a big effect on some of the results. So yeah, I think some of the things I'm hoping to do in future are to take some of the outputs from the magma ascent model and put it into some sort of eruption model. And it might be at that stage that I sort of have a play around with that conduit radius and see, you know, what sort of different eruptions that could produce.
Cool, thank you.
Marissa, do you have an event eruption model in mind?
So I've been looking at a couple of different ones. So there's a terrestrial model called EJECT, which is mostly used for like probabilistic studies, thinking about like mapping out hazard zones around different volcanoes. But it's quite useful for just seeing, for comparing with say like just different satellite images we have of like the furthest extent that the different pyroclasts could go to. So yeah, just something, quite a simple like ballistic ejection model would probably be suitable, especially because, yeah, I'd probably assume that there isn't too much of an atmosphere present when the eruption is taking place.
That'll be very exciting to see.
Yes, yeah, hopefully I'll have time to do that during my PhD.
Well, I think that if there aren't any other questions, I think that we can give everyone about a 15-minute break before they move on to their network session of choice. But again, our network session is in room 1 in the conference rooms at Gather Town. Do you have any final thoughts, Wajiha?
No, I would also like to say thank you very much to all speakers and everybody who participated in this discussion. Thanks a lot and have a nice rest of this conference.
Yeah, and thank you again to Ashkan for our excellent IT support as well.
Yes, yeah, thank you.
The recording has stopped.
Thanks, everyone.
Thank you, Ashkan.
Thank you.
Appreciate it.
you.